Hope my screen is visible to all of you, right?
Yes.
Okay, so yeah, so Vivek have some activity doubt. Yeah, please let me know which activity Vivek. Then we'll start with the slide. It is an important slide. I will discuss that.
10.7.
10.7.
Sir, there is very confusion.
So first, will you be
Sorry.
so first will you be clearing the doubts or solving the questions?
No. I am just Vivek have raised in the starting, and I just have a small doubt, so that's why. Otherwise, we'll go with the slide only. Okay.
Okay.
This session, and I will suggest you, all of you, please watch these two sessions for week 10 also. This is a solve with us and this is an open session. Both sessions are like today we are going to do that with the solve with us week 10. But if you see that also, otherwise, if at least please watch this open session, it will clear your more doubts. So that's why it is uploaded here in the portal itself. Okay. So like in week 11 have also, if in week 11, if you see that week 11 have an open session and solve with us session also. Both sessions are important. You can go with there also with the same solve with us. This we'll discuss. And also I will suggest you, please see this open session. This one is important for week 11 also. So it is like once you will see, it will clear your more doubt, clear your doubt.
Hello,
okay,
sir.
It is yes.
Sir, these sir, 10 week 10 is more difficult. I understand while I watch 2 lectures, then after seeing third time, then after I understand.
Okay.
10.7. Sir, CF is also correct. It is a forward edge.
So CF is a forward. So we have a problem, which is a directed graph. Suppose DFS of the is performed, okay, from node A, such that when we visit which of the following are correct. CF is a forward. CF is a forward, right? This is going like this. FD is a backward. FD. F we have and D is here. Is a backward edge. AC is a forward edge. A
Sir,
and C.
Option A and C are correct, right?
A and C are correct. Okay.
But sir,
And
no. Only correct. Third only correct. Check
third
answer.
only correct.
Yes, sir.
And BD is a backward edge.
Wrong, sir. BD is a backward, not forward.
Only third option is right.
Okay, so let's check here. So CF is a forward edge. So if you go with the we can check as how we will check edge is a forward or backward.
Only see the arrow. If arrow is from A to B, then it is forward.
Only while looking as arrow is will decide the forward or backward. No, it is not true, right? It is not like if you go with like this, okay, if you are going with A and B, okay, then C.
Yes.
Backward edge, sir, makes a cycle, no, sir?
So backward is actually for, it is responsible for the making a cycle.
Yes, sir.
Backward is generally responsible for a cycle. So CF is a forward edge is here is saying, okay, so this is we have CF. If you go with the A, C and CF, okay, which option is says true?
Third option only.
Only the third option.
Why not 1?
AC is a forward edge. So A and C, sorry, where is A and C? A is a forward edge, BD is a backward, B is and D. So it is a forward edge. Okay, FD, F and D, F and D, which is a forward edge. Okay,
Yes, sir.
and CF, we have a CF
Hello,
is a
sir?
forward edge. Yeah, hello, yes.
Sir, neighboring. Sir, it is saying we exploring its unvisited neighbors in alphabets. What it means?
Unvisited.
It is in the order of like, yeah, that's very important. Like it is such that when we visit a vertex, we explored unvisited neighbors in alphabetic order. So like in alphabetic order means here unvisited neighbors in alphabetic order. Like if A is, then we will go with like
Sir, your
C.
voice is cracking, sir.
Sorry.
Your voice is cracking.
Okay. Just a minute. Is my voice is clear? Okay. Is
Yes,
that
Yes, sir, now it is.
okay?
So now it's clear.
Okay.
No, it is not.
It is not. Still, my voice is breaking.
Now it is better.
Okay. So we have A and then B. So it is saying we explore its unvisited neighbors in alpha. Like it is meant to say like first go with the A, and then we'll go with the in direction of B. Because from A we can go C, but in alphabetic order we want. So that's the meaning of we will go with the unvisited neighbor in alphabetic order. Okay. First we will go A, then B, then C, and then we need to go D, right? So how we will go? Then next is after B,
To D.
then which
B to D, sir.
B to D will go, not C. That's why it is going to be a backward edge. Is
Not
it clear now?
No, sir.
See, we have to explore unvisited neighbors in alphabetic order. So first, if we start from A, perform this DFS is started from A, and we go with the alphabetic order. Is this
Then
clear?
B,
We'll
sir.
go with the alphabetic order. That's all.
Hello, sir.
Yes.
Sir, we go from A to B, then from B to C, then we
Yes.
come from C to again B,
No.
and
So
then
from
after
if we go with the C, then we have to back here. So from C,
Okay,
if we are
okay.
going, so if we are going with the first, we from A we started B, and then if we go with C, and from C we have to back, right?
yes, sir.
If we
Sir, but
if we are doing
DFS
DFS, then back, then D, because we cannot go with the C.
Yes, sir.
Sorry,
I
F, because
understand.
alphabetic order we want.
But
Sir,
sir,
DFS travels to the end of the path, no?
sir, how you decide that CF is a backward? I not
Just
understand
a minute.
this. Sir, we not go through CF and we decide we only just say that CF is backward. Why, sir?
Let me write here. So we have.
So if you maybe discuss the solve with this question first, then maybe we can get clearer ideas, sir.
A is here. Yes, just a minute. Just yeah, and that is B, and this is C, and we have this one, and then this is D, and this is F we have. Okay, by this is the graph we have. Okay.
Yes.
So if you start DFS, then from here we'll go B, and from B where we will go as the in alphabetic order we have to go, then
C.
we will go C, right? So A and then B and then C, but from C we will not go F as because we want to go in alphabetic order. So we will start backing. Sorry.
Sir, but only unvisited, we have to look for alphabetical order, no, sir.
Yes,
Not
unvisited.
understand.
Well,
Unvisited,
DFS does not continue till end of the path.
Yeah. You don't need to disturb the path that you're going. It's only when unvisited queue that you will have to take the
Sir,
alphabetical
it's
order.
when you want to take the decision between two vertices, that which one to explore first.
Sorry. Could you repeat, please?
Sir, in DFS, when a vertex has two paths, then only we try to figure out alphabetical order. No, sir.
If you have, yeah, then we have to go with the alphabetic order.
हाँ तो सर C के पास तो सिर्फ F ही जाना है ना, C से कनेक्टेड तो नहीं है.
Okay. No,
Sir,
just
it
a
is
minute.
from sir. It is from F
This
to
time
D.
I'm
Sir,
missing something. That's why
F
I'm
to
unable to.
D.
The answer is actually correct. I'm
Sir,
missing something.
hello,
Yeah.
sir. Sir, you
Yes.
do. Sir, you do
Sir,
wrong.
the answer is correct because A to C is the only edge which we are not using. That's why it's forward edge.
Sir, you wrong. Write the wrong arrow. From F to D
What
is correct.
forward and what is backward edge, maybe by end of the class, or if you have time now.
Yeah, we'll discuss. Yeah, we'll discuss. Yeah, let's discuss the. Yeah, this is this side we have. Okay, we'll discuss. Okay, I'm something missing. That's why I'm confused. I got confusion.
Sir,
Okay? We'll
sir,
discuss.
can I say something?
Yeah. Yes.
Actually, this forward and backward edges are non-tree edges. We have to consider only the non-tree edges as a forward or backward edges, actually. So
Yeah,
this CF will.
That's the answer. That's the answer. Yes.
So this CF will be a tree edge, actually. So we have to see the non-tree edges. Then that answer will be AC.
Yes, correct. That's the answer. That's the single answer.
Hello, sir. But
Yes.
tree edges
This is
are
a
in.
non-tree, sir.
No, this is a tree edge. If you again, yeah.
Hello, sir.
Yes.
Sir, but we see tree edges in BFS. In BFS, we are going through a trees. We make trees.
But
Just
in
like
DFS also, when we will say a forward or backward edge, the forward, backward, or cross edges are non-tree edges. Non-tree edges. If you see the definition, those are non-tree edges. If you start DFS from A, so if you suppose you are starting from DFS from A, so from here you will go B, okay, then C, okay, then F, right, and then D. So see that this is the tree we have, right? This is the tree we have.
yes, sir.
And this is, so this is a tree edge, right? So that's why that is not coming as a forward or backward edge. Yeah, I just missed that. Okay, I just missed that. This is the one single answer, as
What,
the Srinivasan
Sir,
said.
we cannot say CF is a backward or forward, right?
Yeah, so we cannot say.
Okay, that's why it is not correct.
That's why that option is wrong.
Sir, just like there is also a one, just like there is also a one problem in which there is misunderstanding. 10.6.
Okay, we'll discuss. Okay, we'll discuss that. Let's discuss
You can describe a proper way what is forward edges and backward edges.
Please, sir, can you please clarify this thing first? You just make us understand. When you say tree edges, what do you mean by? Can you draw the tree diagram of it and then make us understand? Perhaps
Can
it
we
will be.
discuss this once the slide will be over? Once the slide will be over, then can we discuss that?
The exploring the unlisted neighbors in alphabetical order. So when we go to like alphabetical order, each of the lines we call tree edges. Right?
So whatever we are going to discuss, can we discuss after this solve with us this whatever we have slide?
Okay, sir. Okay.
And then we'll discuss.
Okay, sir.
Okay. Because we have to finish this slide, and this slide contain more, at least 5 to 6 questions we have to discuss.
Okay, sir.
Okay.
Sir, will you be clarify the concept?
Yes, it will clarify the concept also. It contains the facts. Like here, the first fact we have 3 facts we have with respect to graph, vertices, and edges. Any vertex in a graph having n vertices can have maximum possible degree is maximum, whatever the maximum possible degree is, n minus 1. And the second fact is sum of the all vertices, sum of the degree of all vertices is always will be even. Can you tell me why?
Yes, sir. Because if you take two nodes and you connect both them, and there is a one edge,
Yes.
and the degree of one is 1, and the second node is 1, and if you sum, then you get 2. 2 is even, right? If you take
Yeah, the
3,
in the single word, one edge makes an two like 2 degree, right? One single edge for different vertices is make a 1 degree for another vertex. Sorry, for one vertex and 1 degree for another vertex. A single vertex, a single edge makes an important or play a crucial role for between two vertices V1 and V2. Here is one.
This is for
degree
non-directed
and there is
graph,
one
right?
degree. Sorry.
This is for non-directed graph, sir.
For all these factors for non-directed, undirected graph. And if two vertices in a graph have degree n minus 1, it means there will be no vertex with a degree 1. Always will be degree greater or equal to 1. It will never be a 1. Okay, if two vertices in a graph have degree n minus 1, simply we can also easily we can verify it, right? If we have 5 or 2 or 3, whatever the vertices we have, if two vertices have n minus 1 degree, so surely two vertices connect with the every different vertices, like every accepting that it will connect with the another vertices. So that's why degree will be always greater than or greater than 1, strictly greater than means it will be never 1. So this is 3 important, and this on this fact we will going to solve a problem, which is this next one. Okay, we have a graph G with vertices A, B, C, D, and E. 5 vertices we have. We write down the degree of all vertices in order of A, B, C, D, E. Okay, this order is written in the form of A, B, C, D, E. Okay.
So can you go to the previous slide for just a minute, sir?
Sorry.
For previous slide, can you just go for it?
The previous slide says
yes, sir.
The maximal possible degree for every vertex is degree. Maximal possible degree is n minus 1, any vertex. And the second is sum of all degree. Sum of degree of all vertices is always even. And the next thing is if two vertices in a graph have degree n minus 1, then it means there will be no vertex with degree 1. Now we have this. So which of the following is the possible listing of the
number of vertices.
Sorry.
N is the number of vertices.
Sorry. Could you repeat, please? I didn't get.
No, N is the number of vertices.
Yes.
Oh, sorry, your voice is not clear to me. That's why I am a bit confused.
No, sir, I got it clarified.
Okay, so in this problem, we have which option is going to be give the correct or possible listing out of the degree. Okay, you have to choose which option give the possible listing of the degrees. Is that 4,
No
4,
join
4,
PD code?
No, there is nothing on joining PD. So you just need to write on chat. Once you get the answer, you please write in the chat. Please everyone try to answer, and please everyone try to solve this problem. This problem you can use whatever just now we uses the 3 facts. Using those facts only we can choose the correct option. And whenever you are posting, try to direct answer me. That would be good, because if it would be everyone, then it's look like everybody can see that. Is everyone trying? Anyone is trying, or we are going to discuss the solution? So if you are trying, I will wait.
Completed.
And
Sir, I completed.
Move
You can do.
forward.
Sir, show the answer.
Will the recording of this will be available on YouTube?
yeah, this is live, right? Just a minute, let me check it.
No, I'm
Just
asking, sir, will the recording of this will be available?
Yes, yes.
Yes.
So how many questions do we have to this?
6.
It will be live. Actually, it is going live. Let me check once.
No, sir, it will be saved.
I don't see any link on YouTube, sir.
Okay.
Sir, there is a link on YouTube.
Yeah, I think so. If you go with the direct on
No problem, sir. If it
on
is
the
available,
BS degree live.
if it will be available, then it's fine.
It will be available once the session will complete. Myself I will update in the calendar.
There is no link in the
Okay,
calendar.
so let's only there is no link. This is I'm just looking, somebody has posted the link in chat.
Sir, if you go to the IIT Madras YouTube channel, then there is already a session, live session is going on.
Yes, that's a process only. If you go with the BS degree channel, IIM online BS degree, then you will see. So let's discuss the options. So in the first option, here is the stepwise it is given. So we are going to cancel out. The option wise will go, because there is more possibility whatever the given, but we want to choose the correct option only. So in the whatever the options we have given, like the first, in the C option, the option C is 5, 4, 2, 3, 2. Okay, but we know a fact that if you have 5 vertices, then each vertex or any vertex have at most n-1 degree. But if you see the C option, a vertex which contain this says that vertex A have 5 degree, but it will never possible. So that's why this C option is going to be cancelled out. Now similarly for B option, sum of all, like here whatever the degree is written, which is here 2, 1, 1, 1, 2, 5 for 5 vertices is written here. If you sum out, it's give odd, but we just now see the fact that if you sum out the degree of all vertices, it will be even. So that's why this option, the option B is going to be cancelled out because this gives the sum as a odd. It should be even. Now in option A, if two vertices in a graph have n-1 degree, it means there will be no vertex with degree 1, right? Just now we see the fact that each vertex have at least degree greater than 1. If you have two vertices, have degree n-1. So if you see that option A is 4, 4. We have 5 vertices and 2 options. The degree of A and B is 4. So it means if two vertices have degree 4, then, and now if you see the degree of D and E, which is 1 is given. But it should never happen with as we know the fact that if two vertices have degree n-1, the degree of each vertex is greater than 1. So that's why A is going to be cancel out B and C, and only the D option is giving the more possibility as we have with the fact, which is 4.
Sir, in the D option, there are two sir, and there is one
There are
also.
two. So it shows the fact we have that n-1, not 2, 2. It is only for n-1 vertices.
Okay.
Okay.
Sir, hello, sir.
Yes.
Sir, in the question, they not say that you have to connect each and every vertex. So why not B is correct?
Why not B?
Yes, sir.
B is not correct because of this give the sum as a odd. If you sum out, it give the odd, not even.
Okay.
Sir, it means the D option is correct because like when we think of degree, we should be thinking in a way that one vertex is connected with how many vertex?
Yes. We have to think that this is the fact for any graph, like for any vertex.
No. The 3 points, sir, the 3 points you mentioned is correct. Those are the rules in the graph theory. That is correct, sir. What I was asking is a very different thing. My point was like when these kind of problems are there, then we have to think in a way that whenever we think of a degree, I personally think, and this is what how I studied, I personally think that one vertex is going to connect it with the number of vertex, and that is how I assume a degree to be. Like to understand. So when it says 4, 3, 2, 2, 1, are you suggesting that okay, fine, the vertex A is going to connect with the 4 different vertex, and the B is going to connect with the 3 different vertex? Is it how it is going to be interpreted?
Yes. It is how it is interpreted.
Okay, sir.
If one vertex is connected, like 5 vertices we have, the vertex A is going to be connected with all vertices. Now, if you B have degree 3 means already A have connected. Now, if you start listing out the graph is, so whatever the answer we have, like suppose here is A, B, C, D, and E we have. So as here says A is connected, A have 4 degree. That means A is connected with all
the 4 vertex.
Now B have degree 3 means B is already 1 degree. Now we have to connect with the rest 3. So anyone, like you can connect with 3. So now B have degree 2, and now this is going to be. So B is could be possibly this or different also. You can connect with the C also. Now what is given that? The next one is given C have degree 2. So we have C is here. So C have degree 2. So that means you can connect here. So now C have degree 2. Now what is the possibility? And D have degree 2 also. So D have degree 2. That means we have wrongly connected here. So we have to do something else, like you can connect by this. This is going to be correct way. C have this one D and D have degree 2. So D have like this only. So something we have to, like, we can graph with the possible, like whatever the fact, like under this criteria, whatever the fact we have, using that only going to be D is going to be correct one. Okay, and E have degree 1. So E have degree 1. Here is E. So correct way we have to go. Here is E have degree 1 only. So this is the only this one, and this. That's all. and this is going to be, I think so, like this.
So basically, we talk about the possibilities.
Yes, possible. Yes, possible. This is one possible graph.
Yeah.
There may be different also.
Thank you, sir.
So now next is adjacency matrix, a matrix with the rows and column labeled with the graph vertices, and all the entries in the are either. So what is the adjacency matrix? Like writing to be the, you could write like this. You will form a matrix like this, and suppose we have this graph. So suppose this is A, B, C, D, and E we have. Okay. So if A, B, C, D, E we have, so then now whatever the row like you wrote here, we just wrote here. Similarly, A, B, C, D, and E would be written as here. Now, if there is a edge, then the entry is going to be non-zero. Means only one we can write. Non-zero term is going to be only one.
So this matrix is made for directed graph, right?
Sir, if A and B are
For any graph.
Sir,
It
if
could
A
be
and B are,
directed or indirected. Sorry.
sir, if A and B are
Only
two
one
vertices that are
person.
connected by an edge, so should we enter the value of the matrix
Yes.
as one, sir?
If
So
A
should
and
it
B
be taken as row and column or column and row?
yeah, it could be like it is a if it is a undirected, then it could be a so it will be a symmetric matrix, means you can change the row and column. But if it is a direct, then you cannot change the row and column. You cannot, like, you can shift to here and like this. It isn't written in proper order. Like here is, this one is directed graph. So we have between the A and B we have a graph. Sorry, between A and B there is an edge. So that means here this is going to be, you, how you will start filling this number is, you can start with the A, and where is the edge B is connected with that. So this here is going to be 1, and there is C also. So A is connected with the C. So here is 1, and rest are, there is no edge with the D and E is whatever we have. So this is going to be 0. And A with always will be a here, at least for this course. Like here is the loop kind of thing. We are not going to think about it. Like A to A means here a kind of loop is in the graph, but at least for this here we are not going to do. So for A to A always will be 0. You can think.
Hello, sir.
Yes.
Sir, in the lecture they say that known tree edges make a cycle. What
Yes.
it means? Known tree edges make a cycle.
Non-tree edges.
Can make a
Non-tree
cycle.
edges means like here we just now make like here is, this one is DFS, right? DFS, we started DFS and start here A and B. So this form a tree. Whenever once you will do BFS or DFS, it will give you a tree, right? It will give you a tree. Tree means what? Every edge is connected, okay, with the, like the tree is called, there is no cycle. If there will be a cycle, then that is not going to be a tree. Cycle, if you see the definition of tree is a graph where there is no cycle. That's the meaning of tree. Okay,
And
we'll
sir,
discuss that. So here is as that in that problem. So we'll discuss it. Okay, the tree or that the backward forward edge we'll discuss. Let me finish this slide. Okay, let me finish. We are discussing on the adjacency matrix. We are trying to write the adjacency matrix for this graph at least. So this is the process to write. Like B is now
BA0.
Between B and A, we have here there is no graph. Here is this is a directed graph we are trying to write. So that's why it is going to be 0. Now B is connected only C and D. So C is going to be 1 and D is going
So
to
will
be
there
1.
be a tree diagram for a
are
cyclic
going to be
graph,
0.
sir?
So this is the sorry.
Will there be a tree diagram for a cyclic graph?
There will be a tree diagram. Sorry, I am
For a
not
cyclic
getting your
graph, sir.
voice
For a
clear.
cyclic graph.
What is a cyclic graph? No,
When
what
each
you
of
are
the
saying?
vertices are connected to each other.
No, I didn't get your question. Could you repeat, please?
So I'll probably ask it at the end, sir.
Okay, so let me go with. So this is the process to write the adjacency matrix. Okay, Your voice is not clear to me. That's why I'm repeating more time. Like other one can speak directly. And so this is the process. So I and jth entry, like here is. That's now I said that how you'll feel the 1 and 0. So this is the process. If there is an edge, then you will feel 1. Otherwise, there will be 0.
Hello, sir.
Okay. So
Hello, sir.
this is going to be, suppose
Sir, your
we
voice
have a
is not
graph.
very clear, sir. It's breaking,
Yes.
actually. It's
Sir,
lagging.
you are not audible, sir.
Yes.
Hello, sir.
Yes. Hi.
Sir, if a matrix is symmetric, then we can say adjacency matrix.
I'm not audible.
Sir, hello, sir.
Okay. Just a minute. Yes.
Sir, every graph is adjacency matrix.
Now my voice is clear.
Yes, sir. Clear.
Yes.
Okay.
Sir, every
Sir,
matrix is hello, sir. Every matrix,
Yes.
every matrix is adjacency matrix. We can say.
Yeah, adjacency matrix, the definition for adjacency matrix means whatever you have graph, you can form this graph in this fashion. And from here, you can back to the graph also. And where is 1? That means there is an edge between A and B. Like here is, if you say here is 1, that means you have an edge in the graph between the vertices A and C. Here is again the edge between vertices A and D. Similarly here is E and A, here is E and A is here. So that means there is an edge between E and A. Like here you can see there is an edge between E and A. That's
Hello,
the
sir.
process. Yes.
Hello, sir. But can we say matrix of G? Can we say in place of adjacency matrix only matrix?
But generally the word is adjacency matrix.
Okay.
Sir,
Huh?
sir, like, can you just explain the topics along with the questions that are all related to that question?
Yes. So whatever the topic now, just now we discussed the adjacency matrix, no? So the whatever
Yes,
the
sir.
topics or questions will be, before that we'll see some facts or some definitions. So that's
Yes,
why
sir, like-
I was trying to explain you what is the adjacency matrix or how we will write the adjacency matrix.
Sir, and one more request, sir. Like, suppose if the questions which are all planned in this session, it's covering all the concepts of this week 10, it would be so good, sir.
Yes. The probably it will cover the all questions. Like it is jump to the adjacency matrix. But we'll see at least vertex coloring graph, like coloring the graph. We'll see also, and the topological sorting we'll see in this slide.
Yes, sir.
Okay. Yes.
Sir, in the previous open session, sir has completed all the notes that directed, graph, indirected, in degree, out degree, adjacency matrix. But the left one is BFS and DFS.
Yes, sir. That has not been completed yet.
That has not
And
been
their
completed.
applications too.
Okay.
Reachability also done, complete graph, planar graph also have completed, but the last one, BFS and DFS, is not done. So I think if you complete in this class.
Yeah, let me finish, then we can discuss. Otherwise, we have already one BFS also. So while discussing that problem, I can tell you the BFS at least, and
Sir, I
DFS
think
also.
DFS and DFS, the TA sir said that he will be doing it tomorrow, sir.
Sir, D option is right.
So
after the class, it will be good.
So option B.
I have one problem also. While discussing that problem, I can tell you the BFS, DFS both in short. Okay. So please solve this problem. The maximum number of non-zero entries in the adjacency matrix of a simple graph having 5 vertices can be. Maximum number of non-zero entries.
D part.
So yeah, please, if everyone write in chat and direct message me, that would be good. So industry have just given 25. A. Rehearse. This T.
Hello, sir.
Yes.
Sir, if you want to find edges in a graph, then the formula is n minus 1 by 2.
Can we? I will take your doubts. Can you stop and could you please solve, because if we will start discussing, then the slide will not over. No, I will take your doubts one by one. Each doubt I will take whatever you have. But let me finish that. Who wants to be here for at least to see the slide? Okay.
Okay, sir. Sir, only is phone.
In this problem, we have to find out the non-zero entries if we have a adjacency matrix.
Sir, it is a directed.
No, generally, whenever there is no specified, like it is, whenever there is a graph and asking for the, if you think always for any graph, just think for the non-directed, means undirected graph.
Okay, sir.
Please, everyone, try to solve this problem.
Yes, sir.
Hello, sir.
Yes.
Sir, can I ask small doubt?
I will take later.
Sir,
First, let me discuss.
I completed this.
Yeah. So, but when we'll start discussing, then people will be start listening here. No, that's why they will not do the problem. So let's discuss the solution.
Yes, sir.
Yes, sir.
So solution is consider 5 vertices. Like for general, we can think this will work for any. No, so this problem is for any. Just we have information that 5 vertices graph. A graph which have 5 vertices. That's all. And asking for the number of non-zero.
graph.
For a non-directed. Okay, for undirected graph, this should be generally whenever you have a problem, always think for the undirected if it is not specified for.
Just specify simple graph is always undirected.
Yes. So consider a 5 vertices. Generally, we can think A, B, C, D, E. If we have an edge between every pair of vertices, then so this problem is asking for the maximum number of non-zero. Okay. So we'll try to maximize that. It could be minimum also, but we want a maximum number of non-zero entries. So here is the next. If we have an edge between every pair of vertices, then we will have maximum number of non-zero entries in the adjacency matrix. So when there is a possibility that the adjacency matrix have non-zero, maximum number of non-zero entries is when every edge connected with the different vertex. Okay, different vertex. If we have an edge between every pair of vertices, that's the meaning. Every edge, every vertex is connected with the edge, an edge. So now, like here is, we can think
Complete
so,
graph. No? This is a
yeah,
complete
it's
graph.
a kind of complete also, we can think. Now, if you see each vertex is here, mean to say maximum. When it will be maximum? When you can think that each vertex have at least, not at least, each have n-1 degree, means 5 minus 1, which is 4 degree. So here, if you see that this is going to be a, we want to non-zero entries, that means, and in the maximized form, that means each vertex is going to be have degree 4, at least, not at least, the maximum each vertex have degree 4. Then it is going to be the maximum non-zero entries in the adjacency matrix. So for this one, we can form the adjacency matrix, this one. So if you see here A and C, so simply we can think that except the diagonal, each entry is going to be non-zero. Except the diagonal reason is we cannot form there is no edge from A to A. Between A to A, we cannot, there is no edge. Rest all, each vertex is connected with the different vertex. So this is going to be, now we can calculate, or we can count here, or we can write like this also. The total number of entries is, how many entries is 5 plus 5, which is 25. Number of non-zero is, we can see on the diagonal, which is 5. And the total number of non-zero entry is 25 minus 5, which is going to be 20.
Hello, sir.
Yes.
Yes, sir. Got it.
Sir, if there is n minus 1 by 2, then what it indicate? If there is n means nodes and the formula
N is the number of edges, sorry, number of vertices generally, no? M is generally denoted with the edges. N is going to be the number of vertices.
Yes, sir. And the formula n minus 1 by 2, what it indicate?
So in the, something is written, no? What is that?
It shows the number of connection in unidirectional, that is one directional graph.
Directed graph.
Yeah, sorry, indirected graph, that is this is what I said, unidirectional. One direction में जो graph होगा ना, उसमें कितने connections होंगे, उसको
directed means directed in unidirectional.
directed बोलो, आप directed
sir,
बोलो.
Sir, can you make a graph of directed of this, and there is 10 or not?
Directed of this one.
Yes, sir, this one.
So why we need directed?
Sir, there is a 2 formula, n minus 1. In the lecture, the professor write n minus 1 by 2, and in the place of 2 in direction.
विवेकानंद,
yes,
अगर n into n minus 1 by 2 होगा ना, तो arrow एक तरफ लगेगा, simple. n into n minus 1 होगा तो arrow दोनों तरफ लगेगा, या arrow मत लगाओ. Arrow जब दोनों तरफ नहीं लगाएंगे तो बाई डायरेक्शनल है, किधर भी, जिधर वो से कनेक्ट हो, किधर भी जा सकते.
Okay.
ठीक है, तो ध्यान रखो.
So we have a BFS here. When we will perform a BFS, no, breakfast search. So that in that case we will get a tree. That is called BFS tree.
Sir, your voice is not clear.
It's not clear. Okay.
Sir, come close to the Wi-Fi.
Now is it clear? My voice is loud and clear, right?
Yes, sir. Clear.
Yes,
There is an internet issue from your side.
Because of some internet issues, like in this time, generally we have the much crowd on internet. So okay, so BFS tree is generally, what is that? When we perform BFS, we'll get a tree. So original graph and its BFS tree starting with the node A, it shows here. It's shown here. Okay. Am I audible clearly?
Yes, sir. Now good.
Okay. So from A, we are going to be, if you do the BFS, the corresponding tree is going to be this one. We'll see here. both vertices at the level. So whatever, if we perform BFS, we'll get a tree that is called BFS tree. So there is some important fact is here. If in a BFS tree, label, here is the label thing. As we have gone through the lecture, there is a label thing. So let me know that what is the label we have. What is, so I just said that when we'll start discussing the, or we'll do the problem BFS, then we'll discuss the like problem, then we'll discuss the BFS. So what is BFS? Suppose if you have a graph, let's say this is A, this is B is here, and this is D we have. Suppose here is E we have. And suppose here is F. So suppose this is the graph we have, and breadth first search BFS is an algorithm. Okay, this is an algorithm and will perform on the graph and will reaches to BFS tree. What is that algorithm is? That is like if you start the searching, that is a searching thing. If you start searching from A, okay, if you start searching from A, so we have three vertices here. So either we can go this way or this way or this way. Okay, so this is the BFS, and we'll discuss in DFS. DFS has different algorithms. My voice is clear, right? Please, everyone.
No, sir.
Sorry. Okay, I just muted to all. So here is, when we perform VFS means we have three choices. Here is that is called visited thing. From A we can visit. So we can, like here you can think like a pipe is here. I can see the vertex C also, B also, and D also. So BFS means from here A we can visit E, we can visit D, and we can visit B. Okay. Now from once we visited, there is one word explore. Once we visited, then we reaches to B here to explore B. Once we reaches one, we have from A we can visit E, we can visit D, we can visit E. From any one of the vertex we can go now. We have already seen there. Now here is the word exploring. So from A I just reaches to B and start exploring. Okay. So once we start exploring, so so start exploring means here I can visit F, I can from B I can visit A also. Okay, from B I can visit A also, and I can visit F also, but we have already visited because we started from A, so we are not going to concern about A, we are only concerned which is not visited. So I can visit from B is F. So now let me tell you that what is the label is here. So here is from A, I can visit E, I can visit D, and I can visit B. So if you assume here is label as starting point, you can think label is 0. Now from 0 or from A, whatever I can visit, that is going to be, suppose here is label is, if you assume label is for this one is 0. So whatever the visit, we can visit the vertices, that is going to be, that label is going to be always added 1. So that means here is for B is going to be label 1, this is going to be label 1, and this is going to be label 1. Okay, this is the mean of. And now from B, I just start looking this one. Now from I just reaches to B. Okay, I started exploring B, and from B I can visit F only, as it's already A is already visited. I can visit A also, but already A is visited, so I can visit F. Okay, and then so that means that the label is going to be for this one is what? The label for is this one is going to be
P1.
whatever the label is, this one added with that. So this is going to be 1 plus 1, which is 2. For the label is F is going to be 2.
Sir, how the
And
level of F will be 2, sir?
how the label is, see from A, see from 0, from where we started, we assume the label is 0, and from A I can visit E, I can visit D, I can visit E. So from A, whatever the I can visit, that is going to be whatever the label is previous one added with that. So that means we have label is A is 0. So that means label of B is going
But
to
if
be,
you are adding up label 1 and 1, sir.
sorry,
A and
adding
B.
the label.
So for labeling F, you're adding label of A and B, sir.
So here is not, for F is not going to be 1 plus 1 is here. Whatever the label now we have this B, I can visit from B, F is only. So whatever the label for this one, I just added 1 also. If you go through the lecture. So in the label of B, I just added 1. Not here is the 1 plus 1 is happening. Here is whatever the label we have. If the label of B is 2, then the label of F, I am visiting F from B. So label of F is going to be 2 and then plus 1. In that case is 3, but we have label of B is 1. Okay, so that's why it is going to be label of F is going to be 2. That's the meaning here. The label increment, you can say this is the label. And now once we visited the F, okay, now from F, so see this is the algorithm, no? Once we visited, now we'll back and now start exploring D. So this is a algorithm. Let me explain you the algorithm is that is called visiting, the visit thing, and there is a queue. Okay, there is a queue which is a box we have. Okay, and this is the visiting. So let me write here B, 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 C, D. So
Hello,
what
sir?
is the algorithm? Yes.
Sir, by pre and post method, sir, discuss. Can we solve by pre and post this labeling?
No, pre and post is for DFS, not BFS. Okay.
Sir, sir said we can use for both DFS and BFS.
Okay, but sir said, but for at least for this year, we are going to discuss for only DFS. If it is sir said, no issues. Because if he said, but he didn't discuss, so I am not going to discuss that. So for at least for time being for this course, you can assume that for pre and post is for DFS only.
Okay.
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 Sir, I have a doubt, sir. In BFS, it goes level by level. No, first from A it reaches to B, and after that it will go to A and reaches D, and after that one level is explored. After that it will go to the next level. F like that only
Yes,
it would
yes.
be there.
Yes. This is the level wise we can start exploring. So let me write the BFS tree now. So for this one, the graph BFS tree is going to be what we did from A. We visited E, we visited D, and we visited B. These three things we did right once we started BFS. So from A, I visited E, I visited D, and I visited B. Now, so you can assume here is going, so not assuming, here is level 0 and this is going to be level 1. Now, I reaches B and start exploring B. Okay, I reaches the level B vertex and start exploring it. So once I started, then I explore. So from B, I visited F. So here is now level is going to be 1 plus 1, which is 2. So now from F, we already explored, like from once we explored B, we visited F. Okay. Now we are done with B. Now we'll go to D or any one of them. Okay, any one of them. So I just go to D, and from D I start exploring D. So I see that only F, which is already explored, which is already visit. Okay, from B it is already visit, and from another side which is E, which is already visit from A, and in A we have. So whatever the from D we can, is all vertices already visit from D. So that's why we are not going to do. Now we are reaches to F. Sorry, E is here, and again E. We start exploring E. So from once we start exploring E, we can visit A and D, which is already visited. That's why now we are going to end our so we did the level 1 exploring. Now we'll go to the start exploring F. Okay, this is the now once we did exploring thing, we explored all level 1, 1, 2. Okay, now we'll start exploring F. Okay, now from F we reaches F and start exploring. So once we start exploring, the only visit we can B and D, which is already visited. So now it's ended this algorithm. That's the process here algorithm. We ended the algorithm. Now we have the BFS trees kind of. This is one BFS.
Hello, sir.
Yes.
Sir, if there is a one node also after E, G, right? After E, there is G. Then
Yes.
what after G, right?
Yes.
A, E, and G. No, sir, not here. From after the E, after E, connected E to G.
Okay.
Yes, just like it.
Okay.
And then what is the label? Is it 2 or it is 3?
Yeah, so this is going to be label. So from E, we can visit G, right? So again, the label for this is what going to be whatever the label of previous one, and then added that. That means
Okay, fine.
so F and G are of the same label.
Understand.
Okay. This is the meaning. So on the label, we have a problem here. So what is the some fact we have? So what is the fact? Both vertices at the label I in BFS tree, if two vertices are at the same level, then there is a possibility or they may be connected by an edge. So as here we can see it here that if so here is there is no edge, no, they are all on the same level, but there is no edge. No, here is one edge, no, E and D is on the same level and there is an edge, and B and D are the same level, but there is no edge. So that's why the fact is written. If it is the same level, then they may be connected by an edge. Okay. If there is a difference between two level, here is what is a vertex at level I and a vertex at level I+1 in BFS tree. That means there is also a possibility with an edge. Now, like here we can see this level of this one is 2 and level of this one is 1. So there is 1 and this is 2. So there is a possibility, no, there is an edge. But similarly, if you think with respect to E, there is no edge between A and. So there could be an edge or may not be.
Can you please
but
scroll back?
There is one, sorry.
Sorry, sir. Can you please scroll back to the previous slide? Yes, sir. Thank you.
And the next one is, the last one is we have a vertex at level I and I+2. In the case of I+2, then there will be no edge. They will not be connected ever. If the level difference between them is 2, then there is no edge in between them. Like here you can think this one. In the BFS tree says, okay, in the BFS, like here is the level is for this one. Like here we can think, here is what is the level of A is 0 and what is the level of G is 2. So here is the level difference is 2. So also we can think there is no edge. So if level difference is 2, then in that case there is no edge in that. Okay, so this is the surety from the BFS tree we have. If the level difference is 0 or level difference is 1, then in that case there is a possibility that there is an edge. But if level difference is 2, then there will be no edge. Now let's move on. What is the DFS now? And also I explained what is DFS, how we'll start the DFS, or what is the level in DFS also, and what's the DFS, which is BFS. Now let's think about the DFS. On the same graph we'll do.
Hello, sir.
So this.
I have one question. Can I ask that?
My voice is clear, right? Yes, am I audible? Yes.
So
yes,
in that
sure.
BFS tree, can it be used to find out the cycles, right? It can be used.
It is actually this is an algorithm, no? So BFS and DFS is both for investigating the graph. It will properly investigate where is the connect, these are connected, where is the cycle. It is proper. It is these two are actually an algorithm to investigate the graph. Yes.
And BFS tree is used to find out the shortest path, and the DFS also can be used to find out the shortest path. Or the DFS can be used to find out the farthest path as well. But BFS
path is generally for shortest path. We'll see a week 11 content where you can see the shortest path algorithm. Some very complicated algorithm were there. We'll discuss in the. That's why I suggested you please watch that session. No, that which is the count have already taken.
Hello,
that.
Sir.
Yes.
Sir, DFS is opposite of BFS, just like if we do leveling and we say I plus one has, if they have same level, then we can say there is an edge between the two vertices. Can we say this is opposite of DFS?
No, no.
Can
Generally,
you
there
so
is
can
no, whatever
sir,
we
can
have information, we cannot say with the thing that there is an edge
sir,
because there
can
is
you
no
show
label, no?
sir,
The
hello sir,
DFS doesn't give the label.
sir, can you show the slide, black slide of BFS?
Yeah, yeah, okay. So that's the
No sir,
DFS is
BFS. Sir, previous slide, BFS. BFS.
yeah, this
Previous
is
one.
BFS.
Yes sir, yes sir, this. Sir, there is saying I in a BFS may have an edge. If suppose that this is a DFS tree, can
Why
we
you
say
are
first?
confusing with the DFS? DFS is different algorithm and BFS is different algorithm. Don't match. Okay, there is no label. There is no pre-post. Okay, for at least whatever we DFS is a different algorithm. Okay.
Sir, there is
For
a
that, if
question
there
just
is an
like
edge, we'll see there. Okay. So we are not going to also assume for that what will happen in the DFS. Okay. Both are totally different algorithm. There
sir,
is
but
no
there is
label in the DFS. There
but
is
sir,
a pre-post number.
sir, there is a question just like it. Inactivity
Okay.
question.
So there is a possibility that that same tree is asking for the BFS. Yeah. Question could be
DFS.
asked like, if it is suppose this is a BFS or a DFS tree, can we think for at least suppose this is a now DFS tree and solve the problem? But
Yes, sir.
there is no connection in between them. Whenever you have that problem is asked for BFS, you can think the label and you can think for the edge. But
Sir,
whenever that problem is asked for DFS, then you differently think. Yes.
sir, in the question there is a it is DFS. Suppose that it is DFS tree. And fourth option, if we read I plus 2, then there is an edge, must be edge between the I and I plus 2.
So
If
I
it
and
is
I
DFS
that in that
plus
case that is a pre-post number is also there, no? So in that case it wrote it is not the word is used label, no? I think so. There will be no word label.
Sir, okay, sir. And at the end I will ask.
Yeah. Okay, so DFS is what about the DFS? So DFS is again a different algorithm. So DFS tree for an undirected graph can only be an edge in the same branch. Here is again the now here is the word branch. So for undirected graph, generally DFS and BFS both perform for undirected graph and have an edge in the same branch. Because if there is an edge between two vertices of different branches, okay, in between if it is in the same branch, then there is going to be if it is going to be because if there is an edge between two
But same
vertices of
branch,
different
same level, sir. Same level.
Same branch means here the thing is like this one, or let me see the next one is this is going to be at the picture. I think so. Here is or okay. Here is the same branch means suppose see DFS is a kind of algorithm, no, which is started like here, then again it is the internet kind of thing. You start exploring, go in and go in. So here is again this kind of thing. It is in the same branch. These two are going to be. This is the mean of here. DFS tree for undirected graph can only have an edge in the same branch. So this is one branch. Okay, this is one branch. There is again a different branch could be. Okay, there is an edge. So this is one branch in the same branch. There is a possibility that there is an edge can be in the same branch. Okay. Because if there is an edge between two vertices in different branch, then the neighbors of vertices must be visited in the order of remove from the stack. That means if it is there is no we'll discuss that. Okay, we'll discuss that. This will be clear when we'll start discussing the DFS. DFS tree for an undirected graph can only have an edge in the same branch. Okay, so the same word is written on this. On this, there is a problem here we have. Okay, so let's discuss this one. So DFS tree for undirected graph can only have edge in the same branch. If it is in the two different branch, then there is no possibility that there is an edge. Like
Can
here,
you show the next
suppose
point,
here,
sir? So for the
sorry.
DFS tree, can you show the next point, sir? Can you go to the DFS tree? Can you show the next point?
Next point is the only this one, no? This is the same word is written.
Yes, sir.
The reason is written. Here is the explanation is, if we have two branches, so this is one branch, so this is one branch, so there will be no edge in between. Okay, there will be no edge. If it is in the same branch, then there is a possibility that there is an edge. If it is like here is the possibility, like here, there is a possibility that this could be a branch. This could be an edge. Okay, I just differently said here. So here is, this is one branch and this is one branch. So suppose there is another and next one is here. So there is a possibility that there is no edge. There is a possibility not, there will be here is no edge in between these two vertices, because these two are in the different branch. Here is in the same branch means this is the mean, like there is a possibility that there is an edge between this vertex and this vertex, or this vertex to this vertex, or this vertex to this vertex. This is the mean of that word. Okay.
Neighbor means, neighbor means.
Neighbor means, you know, the neighbor for this one is what? Neighbor for this vertex is what? What are the neighbors for this vertex? This one, and this one.
Sir, for B, there, what is the neighbor B and F?
So neighbor for B is going to be F. Here is D and A. So neighbor of B is this one, this one, this one.
So, sir, it is just like a BFS.
So what is now, let me tell you that DFS is. DFS is, suppose we have a graph, this one, okay? This is undirected. So again, let's start from A, okay? So if you start, here is again the visit and explore, okay? So if we start, here is from A. So assume, suppose I am started from A, which is A is visited now. Now I start exploring. So I just reaches to E. Now E is visited and I start exploring E again. So I again start exploring E again. So I can go this way, but we cannot go back. We have already unvisited vertexes here. So we will go here. Okay. So here is this one. Okay. Now from D, I visited, from E, I visited D and I start exploring D now. So I can go this way or this way. Suppose I choose this way. Okay. I suppose this way. So I start. No, sorry. So this is already visited. No, from here, this is already visited. So we cannot go this side. Now I can go here or here. Either I can go B or I can go F. So suppose I just go to B. So here I just start. So from B I visited, from D I visited B here and start. Now here I reaches and start exploring. So either I can go here or here. So this is already visited. So unvisited vertex is this one. Now here we can go here. So from here, the unvisited vertex is this one. I just unvisited vertex is this one. I just here from B, I can see this one and it reaches to here and start exploring this one. So from here, I can go this way, but here is already visited. I can go this way. It is already visited. Okay. So now here is start backtracking. Like here is, now we'll back to here. Start and then back to here and then back to here and then back to here. So what is the DFS tree we have? DFS tree is, we just started from A, then we reaches E, then reaches D, and then B, and then F. So this is, sir, we have the.
Hello, sir.
Yes.
Can you take an example?
So here now this is by example I am doing this one. No? Another example you are saying.
Sir, for edge, how can we edge between neighbor or not?
Sorry.
For
between?
DFS. For DFS, can there is be edge between the nodes or not? Can you take example of this?
Okay. So here, let me finish this one. So this one is we have, so see this edge, there is no importance, there is no importance. Here is, there is no importance of this one. There is no importance of this one. So these are the edges we have. Okay, there is no importance for this one, or this one. So for, okay. Just a minute.
So where is E in the tree, sir?
Sorry.
You haven't tried E in the tree.
Oh,
The
here is
node E.
This one is E. This one is. Now, there is a possibility of an edges. I have to take the another example. So which is, suppose is this one, or suppose this is A, this is B, this is C, this is D. We have E, then this one, and this one. Suppose this is the graph we have, okay? This is the graph we have, and we started DFS on this one.
Hello, sir. Your voice is breaking.
Suppose from A, started A. Again, I started from A. So, yes. Okay, just a minute. Now is it clear? Now is it better?
Yes.
Okay. So suppose from A I started again. Okay. So from A I visited B and I reaches to B and start exploring this one, B. And from B I just go to I have to make a difference. So suppose is this one. I have to erase this one. Okay. Then the branch will become here. So I reaches to B and start exploring B. So I can go D or I can go C. So suppose I just I visited C here and start exploring C. So from C, A is already visited, B is already visited. So we start backtracking. So we reaches to backtrack here and reaches to B. And from B, as you know, in the internet, whenever you have a page here, okay, you went inside and suppose there are list of some link is there, you went to here and there you explored this one, and suppose there is a link in that and you went to there, okay, again start exploring, and suppose the page is ended. So how you will go back to here and back to here and then back to here, and then next page you will go to start searching, and then again go inside of that and start searching something. And if the
In
page
Excel,
is
it is
ended,
there, sir.
sorry.
In Excel, there is one option, sir. If you click there will opening nodes one after one.
So as the same as in the internet, you can see in the Google also usually we search. If once the page is ended, then we will back to the page, and then whatever the another link is there, we can go there. We'll go to from there to that link, and then again start exploring that link and go in. And once the page is end, we'll go back and back. Suppose for this one is another link is there, so then here is we'll go to the another link and start exploring. The same is here, exactly the DFS that as you explore in the internet. Okay, so as here the page is ended now, like I started exploring.
Backtrack to A and then we'll check out for D and F, right?
Then we'll go to here the D, because the same is I started from A. Okay, I went to a link here. Okay, and from link I just reaches to another link. From B I just reaches to here, and then the page is ended now because it's already seen, and this one is already seen. Okay, this one is already seen, so we can now back to this one, and from here we have some another link, so we will reach here. Okay, we'll reach here and then start exploring this one, and we go in, and again the page is here because this one is already visited. So again the page is end, then back to this one, then back to this one, and then the starting point, and stop the exploring. So what is now the branches, or what is going to be the DFS trees here is the same, like A and then B and then C. Okay, then back to here this one, and then D and then F. So here is A, B, C, D and F. Now see, this is two branches here we have. Okay, this
So
is two
shouldn't
branches.
we connect AC and AF, sir?
AC. So so this is a DFS tree we got. This is the DFS tree we got here. Okay. Once we start algorithm on this graph, we got this DFS tree. Okay.
So but why should we connect AC and AF?
Hello, sir.
Sorry. One.
Sir.
So why
Sir?
should we connect AC and AF?
Sir, I have a doubt. Like, it wouldn't be there like A to C, then C to B, and B to D, and D to F?
Sorry. From A to C. There is a possibility that there is another DFS we can possible here. So what is that? From A to C we went. So from A to C, from C to D, C to B. Okay. And then again D, because here is A to C and then D. Okay, then D to F. Okay, so this is one. So again, then this is the end page, ending page. Now we start backing here to this, and then this. So this is another DFS tree.
Hello, sir.
So this is another DFS. So for single graph, there is a possibility that different possible DFS tree you can find.
Hello, sir.
Yes.
Sir, you see the DFS tree in the right and uppermost graph. If you start from D, then go. If you start from D and then go to B, and then go to A.
For this graph.
Right and uppermost. Yeah,
this one. So this is the tree, no? This is the DFS tree of this one.
Sir, this no DFS tree. You write both. Sir, right in the right side there is a graph. Stop the
This
screen.
one.
Right side.
This one.
No.
Right side.
Right. Yes, ma'am. This one. If you start from D, then you go to B and then you go to A, and again you backtrack to B and to go to C. Then there may be an edge between A to C or not.
So there's a possibility that there is an edge between A and C. So see, what is that? If you are saying from D, just a minute.
Sir, you not write an edge between A and C in the
see that
right graph.
There is actually going to be an edge. So you said from D, no? So let's do from D. So from D, okay, I just reaches to B, okay, and from B you said A. So from A, as they start exploring, we are doing the exploration, no? So from here, A we reaches. So we will go to the unvisited vertex, no? So we have already unvisited because we have to go C, because this is the process of DFS. Yeah.
Hello, sir.
This is the process of DFS.
Hello, sir.
Yes.
Sir, if you backtracked from that point and you go to another branch, and you backtracked from that point and you go to the other point, that point and other point is connected, there may be a edge or not. Are you getting my point?
No, so you have to backtrack once you don't have a once you have dead end, then you are only the unvisited vertex, then you have to go there and visit that and explore that. Am I audible clearly? Am I audible?
Your voice is breaking.
Okay. Am I audible clearly now?
No, sir.
No, sir.
No, sir.
Okay.
Sir, just like BFS, I understand the BFS. In the DFS, I stuck. There is an edge, maybe or not. I stuck in that.
That's the I'm saying here. That's the here. Let me explain this one. So between C and F, there is no edge you can see. Like this one.
Yes, sir.
If you see, this is one DFS tree. Between C and S, this is one branch. No, this is one branch and this is another branch. So you can see there is no edge in the original graph. Is there any edge?
No, sir.
Is there any edge in the original graph? No. This is the meaning of if it is in two different branches, then there is no edge. Is it clear now?
Yes, sir. Hello, sir. If in the question they ask there must be an edge or maybe an edge. We write maybe an edge correct or no, must be wrong, right?
So for that problem, which is going to be the most correct one, that is we are going to choose. No, if it is, there is a possibility that there is no, then you will choose that. If it is must be, that means it is a surety that there is an edge.
Use maybe or cannot. Can be or maybe, right?
If you are getting that there is possibility that there is no edge also possible, then you will go with the may, no, because may or may not, may means may or may not.
Your voice is breaking.
So let's solve this problem. It will be more clear once we'll do this one. Okay, suppose we obtain. Okay, my voice is clear now.
Sir, it is better. Sir, it is BFS.
Now it is clear, sir.
Sir, it is BFS, not DFS.
This is for BFS we have. So let's solve this problem. Okay, we will do some. I think the next problem may be on DFS. We'll see there. So let's solve this problem. Suppose we obtain the following BFS tree. Okay, rooted at A. Okay, which is A here, for an undirected graph with the vertices, whatever we have, this is. So which of the following cannot be possibly be an edge in the original graph? This is the problem.
So let's try for two.
Which of the following we have is not cannot be an edge, okay, in the original graph, and this is a BFS tree. Please everyone solve. Sorry.
Sir, what is the
Please
code?
everyone solve this problem.
Third option.
Sir, third option.
Sir, what is the code to join?
There is no code. You just write on chat.
Please write on chat. There is no code. Just need to write on chat. And direct message me. Okay, that would be good, so that I can see who is not who is giving a different answer.
Okay, sir.
Please wait. Let the other people solve it.
Sir, this is a multiple select question.
No, this is MCQ only.
They're completed.
Okay, just wait. Let the people. Anyone else is solving? You are solving. I will wait.
Yes, sir. I'm sorry.
Yes. Yes.
Sir, will you be completed complexity? Will you be discussed?
Complexity means?
Sir, complexity in DFS and BFS.
In DFS and BFS, that is a fact. No, exactly the fact that what is the tree, what is the connected, when we'll see the connected, when see the component thing. That exactly the facts.
Topology sorting.
Topological sorting we'll discuss. That we have problem on that. So let's discuss this problem. Okay, so the solution of it is that option A. In option A, that it says B and K are there is an edge. So B has a label 2 and K has label 3. So if you see here, so or we can say B is this one and this is K. Now if you see that is the label, means here the in BFS, if you see that is the process, like from A I can see D, I can see B, I can see.
So what is the answer, sir?
So here is B. So the answer for this one is, I think there is no edge, no? Cannot be an edge. So E and I, no? E and I see that the level difference is, the level of E is 0, 1, 2. And level of I is what? 0, this is 0, this is level 1. Okay, this D is level 1. And then F is what? Level 2. And H is level 3. And I is going to be the level 4, right? This is
5.
Level difference is 2.
Sorry, this is 0, this is level 1, this is level 2, and this is level 3, and this is level 4. So I and F is the level difference. If you see that this is level 0, 1 and 2, this is the level 2, and this is the level 4. So level difference is 2. So there cannot be an edge. So see that B and K, B and is on the level 1 and K is on the level 0, 1, and this is 2. So level difference is 1. So there is a possibility that there could be an edge in original graph. M and N. So here is M and here is N. So again, see the level difference. The level of N is what? 0, 1, and this is 2. Level of N is 2. Level of M is what? 0, 1, 2, and this is 3. So level difference is again 1. So that's why there is a possibility that there is an edge. E and I. E and I, where is E? And this is I we have. So we just now discussed that there is a level difference is much, or there is a level difference is 4. E and H. E and H again. See that this is 0, 1, 2. The level of E is 2, and 0, 1, 2, 3. The level of H is 3. So again, the level difference is 1. So there is the possibility that there is an edge.
Hello, sir.
Yes.
So M and N, sir?
Sorry, M and N is again edge, no? M is just now you can count. I just here is that's why in a better example I took, and I explained that how the level will count. This is level 1, this is level 2. So similarly, if we go here, the level of N is what? 0. Level of A is 0. Level of B is going to be 1, and level of N is going to be 2. And level of here is M, 0, 1, 2, 3. So level of M is 3. Am I audible? Am I audible?
Sir?
Yes,
sir. Audible.
Okay. Okay.
Sir?
Yes. Yes.
This condition is true for every level greater than 2.
There is no edge if the level difference is going to be more than or more than
for
2
every
or
condition more than 2, more than equal to 2.
More than 2 or 2.
Okay, sir. Thank you.
If level difference is 2 or more than that, then it is going to be there is no edge.
So, sir,
If
what's
it is
the
level
correct
difference
option?
is 1 or the level difference, the correct option is going to be EI. This one, C option.
Yes, sir.
Okay, sir. Next question.
So this class is for how long?
Sir, for
So let me go with the next one, vertex coloring problem. Let's
sir.
finish this. Yes.
For DFS also, sir. Explain for DFS.
So we'll discuss that. If we have problem, we'll discuss that. Okay.
Sir, I'm facing problem in DFS. How can we
Okay,
find
let me finish this one. Let me finish this one. Let me finish. Otherwise, my slide is not going to be finished. So let me finish this.
Okay, sir.
So vertex coloring of a graph. So how we'll color the graph is like very simply we can see. Suppose you have a graph again. Suppose this is A, this is B, C, D, E, and this is F. We have.
So can you please show the slide just for a minute, sir?
Yes.
It's 3, I think.
Or we can see it here for the, I am just making different. So find the, for this, find the minimum number of color required to color all the vertices, okay, of the given graph such that no adjacent vertices have the same color. So coloring of the graph is what? If you color A with a color, okay, then you cannot color C or you cannot color D with the same, whatever you colored with the A. Okay, this is the difference. Like if there is an edge, then you cannot color with the same color. Okay, like if whatever you have colored A, then you can color E, you can color F, you can color G, but you cannot color with the same color C and D. This is the graph coloring. And what is the going to be the number of colors? That is called how many colors is going to be required for color the graph. So this is the problem. So like here, vertex coloring, like we can color here is, if we colored A with the red, so we can color E, we can color G, okay, we can color F also. Here is, so sorry, we cannot color F the red. Why? Because E is already colored. So if we colored E with the red, so we cannot color because there is an edge. Okay. So like here now, if there is no edge, then color that. Like here is, if you have colored this red, so there is no edge which is colored with the red, so you can color J, Q, E. So like this, you cannot color like this all. Okay. Now the next one is like once you colored, so next color is whatever the remain thing, right? You can color that. Like once we have did the coloring of red color, we did the coloring for the graph with the red color, then C, like we can take the another color, which is, we are thinking here green color. So we colored the C and we can color D also because there is no edge. So we can see CD. We cannot color again F because with the same color green, because it is connected with D. Here is H, B and P with the similar, we can see that. Now the next one is, once you colored with the green, now we can take the different color, and now we can color, here is B with the yellow, then we can color F. The remaining color is that you can see the rest one, 2 vertices is only the remain. So for this problem, we can needed 3 color to color the graph. So based on that, this is the problem we have. So this is the question. A company manufacture 10 chemicals. A certain pair of these chemicals are incompatible and would be cause explosion. If we, okay, if 2 chemical will be like mixed, if we mix them, then there is the explosion will happen if we brought into the contact to each other. Okay, below graph. So this graph is whatever we have. shows the incompatibility of the chemical. Okay, chemicals. Each vertex represent the chemicals. Edges represent the pair of. So whatever like here is in this problem, whatever the context is written here, actually the vertex is representing the chemical and edges says compatibility here is that if we mix J and F, that means we can mix them. Otherwise, we cannot mix. Like A and F cannot mix, because if we mix them, there is possibility that explosion could be happen. So that's why if it is we mixing and explosion is not happening, then in that case we are going to connect them. So how many colors is required, or here is the problem, what is the least number of compartment into which the warehouse should be partitioned? Means here is the how many colors is needed to color this graph. So please everyone solve this problem. In this problem just need to solve how many colors is needed to color the graph.
Okay. Okay.
Sorry.
It should be different.
Please everyone mute yourself.
So here we have to find the minimum coloring only, right? So
Yes. How many colors is required, or minimum number of colors is required to color the graph? With the rule, whatever the rule to color the graph is there.
what is the answer, sir?
Sir, is the answer is 4?
3. For the first class. This one coming.
We'll see the answer. Your best to answer this one. We'll see once we start discussing this one. My screen is visible to all of you, right?
Yes, sir.
Yes, sir.
This we have like given 5 colors needed. Abhishek is saying 4 color.
So what is the answer?
We'll see. Once we'll start discussing, then we can see, right? I also don't know how many colors is required. So let's discuss this one. Okay. I think many people have just confused the 4, 5. So let's see how many will be. I also don't know how many colors is required. So like the first, if you take, okay. So in step 1, again the same as coloring. You start taking the color. You can write in place of like you are doing on the pen paper. No, you can write 1, 2, 3 with the color name. Okay, like here you can write 1. Then where I can write 1. You can assume that 1 represents some color, 2 represents some color, fixed color. Okay, like here is, you can say once we colored F, then we cannot color the connected graph, right? So we can color this one, this one, this one. Like here is, once we colored A, we cannot color C, D, E. Only the remaining thing is I. We can color. Okay, once I colored I, we can not color H. So the second step is this one. Okay, the second. Am I audible, right?
Yes, sir.
Yes, sir, audible. Audible, sir.
My voice is clear and loud. Am I audible?
Yes, sir, audible.
Okay. Now in the next step, we start
Sir,
coloring.
can't we color B with green?
B
No,
with
C is connected. C is connected.
See, once we see, that's the problem. If we B color with the B color, this B with the color green, then C we have already, either if we color B, then we cannot color C. So that's the
But then
one
it
thing.
won't be the least number of ones.
No, if you do the color B here, B, once suppose I colored B here with the green, then I cannot color C. But we want a minimum number of colors, so that's why we'll try to do like that, so that we can possible the minimum number of color is required to do the coloring. Okay. So once we do, the next is this one we can do, and finally only the 4 color is required to color the whole graph. Means in the context form, only 4 compartment is needed to store the chemicals without doing the explosion. Okay. So for this one, you can see here the coloring. Okay. Now let's do the next problem. Okay.
Yes, sir.
Here is the next information is about the once we have the coloring thing. No, so how we can solve without affecting, or how many edges we can connect without affecting the color thing. Right, like here is, what is the problem here is vertex coloring, adding of edges, means the word is here. Suppose I did, or I added an edge between A and F, then I think there is not
Their voice break.
There is not going to be effect like here we can see. For example, if my voice is still breaking.
No, sir.
Or is it clear now?
So now it's clear.
Okay.
So can you go
Sometimes
back
it may
to
break.
previous slide?
Okay. You could just wait. Is it better now?
Yes, sir.
So like we can see, if we connect F with the, you can see as the dotted lines is here. If we still connect with these edges, there is not going to be effect on the number of colors. Like here is, we required 3 colors. So still, if we add edges here with the F, here is, if you connect C and F, A and F, still the number of color, whatever the here is 3 is required, is still the same color is needed. So on this problem, we have on this, whatever this is one we have on this, we have one problem. Okay. And then another thing is planar graph. Planar graph means you cannot, planar graph means what? You cannot, if you start connecting, or the edges cannot be like here. I can show you with the example. Here is like this one. If you connect connect C and D. Okay. If you start connecting C and D, so if you do from the inside, then what will happen? It will cross the edge AE, okay, and CF. So in that case, it's not going to be planar. So we can do an edge in the outer side. From the outer side, I can connect, or I can connect the C and D. The planar graph means the edges will not intersect. That's the meaning here, the planar graph. So like on this basis, I think we have a problem. So an incomplete undirected graph is shown here, and number of here is the number of each vertex. Like here is 1, no, here is 1, here is 1. This represents, suppose, a color. So this is a colored graph, you can think. Okay. So denote the coloring of the graph, like 1 is denote one color, 2 is denote another color, 3 is denote another color. So find the number of maximum edges that can be added to the given graph such that the coloring is retained and the graph is planar. That means if we start adding the edges here, then there is going to be no effect on the number of colors. Whatever the color is required to, it is already denoted here. Like here is denoted here, 1 is 2, 3, colored is here already denoted. It will not still affect the number of colors, whatever the number of required colors is there. So here is as a hint is given that try to maximize the inner edges and then draw the outer edges.
Excuse me, sir.
Yes.
Sir, how to get the recording of this session?
It is streaming, no? It is on YouTube.
No, sir, it is actually showing the wrong URL actually.
Okay, then we'll up to it. Okay, after the session, I will update.
Yes, sir. Thank you, sir.
this could be done manually. Okay, there is no formula or something. You have to just think that how I can connect so that the color number of color is still not affected. I am going to discuss the solution because it may take time, because when you start it's actually take time. So let me show you the simpler one.
Class for, sir?
I want to discuss the topological sorting. Only the next problem is one problem is remain. Okay. So like here is the solution is the first, as the hint is rather inner edges and then inner and outer. So like here is we have the graph is, so we can connect 2 and 3 as 2 and 3 with the different color. No, so still we can do with that, right? So we can do 2 3 and 3 1, and again from 2 we can do 2 3 and 2 1. Is it will not affect the color still, because if you have this color, then 3 is still different color and 2 is different color. If it's 2 and 3 is connected, then there is a different color. You can see easily as the condition for the coloring is still retained, at least for once you do the inner edges. Now for the outer edges, if you see that, what we can do, we can simply think that 2 and 3 can be connected. Okay, 1 3 can be connected, or 2 1 could be connected. Still it will retain the number of colors. So now from the outer edges you can do same. 1 2 can be connected, or 1 3 can be connected. Similarly from 2, if you take here, so from 2 either 2 3 could be connected, 2 1 could be connected, or here's again 2 3 is there, so still 2 3 you can connect. Except that if you do all, it will do the intersection. Now if you count that, so if you count, the total is what? 1 2 3 4 5 6 7 8 9. So 9 edges can be done or can be added without affecting the number of colors. Okay. So let's do the next problem, which is on the DAG and the topological sorting. My screen is visible, right, to all of you?
It is visible. Yes,
okay. So DAG, what is DAG? Directed acyclic graph. So directed means here is the direction is given. Okay. Acyclic means that graph will not contain the cycle. Means here the directed graph which will not contain a cycle. In that case, you can call it as a DAG. That is a DAG. For example, here is simply a directed tree. You can say that is a DAG. Sorry, that is a DAG. Or like here this one. A, B, C, D, E, F, or E, F, G. So here is you can see that it just is here in the directed. So direction will be given at least. And in that case, suppose I just made like this. I is here, okay, I is here, and this is the, and this is. So here is, this is not a DAG. The reason is there is a cycle is here. This, and suppose this one is still the direction is this way. This way. So this is form a cycle in the directed graph. So this is not a DAG. DAG means it will not contain any cycle. If you are forming, we can forming like this, so still this is the direction will be, then it is a DAG, because this is not forming a cycle in the direction using the direction. So DAG means this one. So okay, if this is the case we have, so can we sort out? So based on that, we can form a real life problem that suppose you are in the semester exam and these are the exams, like this is one exam, this is one exam, and you are here, okay, and this is another one, this is another one. So based on that, so if you want to finish the course I, so before to finish this course I, you have to do the at least courses how many courses is to required to do, means you have to do B, C or D, E, F. After doing these courses, you can only do this I course. Otherwise, you cannot do. So can we form can we find an order so that, okay, can we form an order so that we can perform, or we can say once I want to do this I course. So before to do I have to do B, then C, and then D, E, or whatever the in between courses is that I have to finish that, and then I can do. So can we find that order? That is called the topological sorting. Am I audible?
Sir, can you please
Yes,
explain? Can you please explain?
Audible, sir.
Yes, sir. Please explain, sir.
Okay. So like here now, directed acyclic graph does not have a cycle. Just now I said that a graph which is directed, okay, but it could not contain a cycle. That is called the DAG. Every DAG has a vertex with the in degree. So there is an in degree and out degree concept. So here is, we can see that here is the in degrees. There is no in degree for A, because here is no like this the direction. This is called outer or outer degree. So this A have the outer degree. It doesn't have the in degree. So that means if you see the in degree of A is 0. In degree of B is what? 1. In degree of C is 1. In degree of, I didn't give here the, let's say this is IJK. This is the vertex J is here. Okay. So in degree of J is what? This is 1 only. Okay, this is 1 only again. For D is also, for F is also. Here is this is F. So for F is again the 1. And for G, we can see that for G is degree 2, in degree is 2. And here is for I, in degree is 1. Out degree of A is what? 3. Out degree of B is 0. There is no outgoing edge. Okay. Out degree of J is what? Out degree of J is again 3. Out degree of D is no, there is no outgoing edge. So out degree, in degree and out degree means outgoing edges and ingoing edges. If you count that, in degree are incoming edges, that is called for responsible for the in degree, and outgoing edges is responsible for the out degree. So here is in every DAG. So if it is a DAG, okay, so that means there will be a vertex with the 0 in degree, and every DAG has a vertex with the out degree is 0. So there will be a vertex. So every vertex, there will be, sorry, in every graph or in every DAG, there will be a vertex where the in degree is 0, and also out degree is going to be 0. For this graph, we can see the in degree for A is 0, and for out degree A is 3, but for B, we can think that out degree of B is 0. So for every DAG, at least it contains some, it surely contains some, for a DAG, it surely contain a vertex which have in degree is 0 and out degree is also 0. Topological sorting and the longest path. So if you have a DAG, so there is two concepts, or there is a two problem based on the DAG, which is called topological sorting, and another is this longest path. Longest path we'll see in the next week. For the next week, for this week, we are going to see the topological sorting. Okay. So topological sorting is write the in degrees of all vertex in a DAG. Okay. So how we will do? Topological sorting is based on an algorithm. So what is the algorithm? Is that first note down the in degree and out degree. So there is an algorithm, and we'll do here at least for manually when we learn the Python, there we'll do in the Python we'll do, but here at least we'll do the manually. So what we can do, like here just now I wrote in degree and out degree. So that's the process while start doing the topological sorting or the algorithm. When we'll start doing the algorithm, we'll write in degree and out degree. Okay. And
Sir,
add the sorry.
Sir, that last slide,
This one.
the degree slide, the diagram we were showing them.
Okay.
The drawing, there was a drawing. Degrees, I was showing the degree now.
Sir,
So till now there is no degree thing. Please if you unmute yourself. So for the next slide, I think so it will show you the degree thing. Like I think this one will see. Okay.
So can you please scroll to the
Okay. And add the vertex U to a topological sequence. Okay. Remove the vertex U from the DAG and update. So suppose you have the 0 in degree. Okay. Here is the find the vertex U which have 0 in degree. Okay. And add in the or sequence like U is just now wrote. Then remove U and update the all in degrees of each remaining vertex after removing the U vertex. Once you remove the U vertex means you have to remove the edges also which is related to U. Once you remove that, then you have to update the in degrees of each remaining vertex and repeat this process from the step 2 till the last vertex in added in and vertex is added to the topological sequence. So we'll see here one by one. Like here is this problem we have. Suresh needs to perform six tasks, namely PQRST. Some tasks needs to be performed after performing a particular task. Okay. In the below table showing column 1 shows the task and column 2 shows the set of tasks that can be performed only after performing the particular task. Like if Suresh want to perform Q and R task, then this could be performed after completing the task P. That's the meaning here this table shows. Okay. The problem is the next one. What is the possible order in which Suresh can perform the task? Enter the letter in order to separate by the comma. Okay, separated by comma. So I think this is the solution part of it. So for this problem, how we'll do the for this? So this is actually what? This is a adjacency list. This is this matrix or this graph is written in the form of adjacency list. So we have to form a graph using this adjacency list and then we have to find the topological sorting. While discussing the solution, we'll easily see that what is the topological sorting also. Please everyone solve this. Am I audible?
Yes, sir.
Okay.
Yes, sir.
Everyone solve this problem. While discussing the solution, try to yourself at least try to find the graph with at least this problem. Then we'll discuss the topological sorting. Once we'll do the discuss, then easily we can find what is the process or how we'll find the topological.
Sir?
Yes.
Sir, can you please tell again what the column 1 signifies and what the column 2 signifies?
Column 1 is says that like if you Suresh wants to perform suppose Q task and R task. So that means to perform Q and R, he have to at least perform or he have already done the task Q. Sorry, task P. Like suppose P is a painting and Q is like wiring or something is that. So after suppose I am saying wiring could be done after the painting. Then this wiring here is first he will do painting, then he will do the wiring of the room of a room or any house.
So P is the prerequisite for the Q and R.
Yes, prerequisite for the Q and R.
Okay, sir. Thank you, sir.
Excuse me, sir.
Yes.
Sir, after the questions, can you explain the concept of independent set and vertex cover?
Yes, yes. Yeah, please let me know once I will finish this.
Yes, sir. Yes.
So sorry to interrupt, but how long will this take, sir?
Sorry.
Sorry to interrupt, but how long will this take, sir, approximately?
Now this is the last problem. This is the last problem. Then who wants to leave can leave. Like wants to be to know whatever we are going to discuss. That is a kind of doubt. Okay. So who wants to be here can discuss. Did you have solved this? Okay. Okay. Please, everyone, solve this.
Excuse me, sir.
Yes.
Sir, I just wanted to ask, sir, out degree, sir, is that what we call an outgoing degree, or is it the number of outgoing edges, sir? That's what we call it.
Number of outgoing edges.
Okay, sir. Thank you, sir.
Prince have solved. Okay. Richu have solved. Subrat, Avinash.
So what is the answer?
We'll discuss. We'll once we'll see the. While discussing, like somebody's have like Richu have posted TU SPRQ. We'll see. Okay.
So actually, because this.
So let's discuss the solution. This is the last one. Real quickly. So. We repeat the given data as
Sir, voice is breaking, sir.
Okay. Sorry.
Sir, your voice is breaking.
Whatever we have data is given, we'll try to graph that. Before drawing the graph, like without drawing the graph, there is a difficulty to find the topological sorting. Yeah. Now it will be clear. So is it better now, na? So whatever we have data, no, this one we'll try to. Still, my voice is breaking.
Sir, now it's better.
Is it better now?
Sir, now it is better, sir.
My screen is visible, right? Am I audible?
Yes, sir. Yes, sir. Yes, sir.
Yes, sir. Okay, so whatever we have data, no, we have to find the graph. Without that, it will be difficult to do the topological sorting. So let's find that. So like that we can form, like here, if you start drawing the graph, okay, for this one, like P is connected with QR, Q is there is no. So here is Q is represent, like it is a represent a dependency, no? So Q is not dependent, Q is totally independent. Sorry, Q is not here. There is no outgoing edge. That means here there is no outgoing edge. For R, there is an outgoing edge for Q. Okay. So we'll see here. The next is the graph would be the whatever the data we have. No, so if you try to graph this one, this would be like here is P. From P there is an edge Q and R. So P is here. So that means there is an edge Q and there is an edge R. From Q don't have outgoing edge. So Q have only incoming edge. Okay. So from R, incoming edge is, outgoing edge is this one on Q. From S, P and R. So from S, so this is S. From S, P is here and R is this one. So outgoing edge is this one. From T, U and S. From T, U and S. And from U only on P. So from U is only on P. So this is the process to find whatever the data, the graph will be this one. Okay. Now the next one is we have to verify that is this a DAG or not, means it will not contain any cycle. So if you verify that this is not there is no cycle, this is actually a DAG. So that's the here in the solution part, we have to verify that it is a DAG. Okay, first, and then next is find the in degree of all vertices in the graph. So like here, write down the in degrees. To find the topological sorting, there is no importance of the out degree, but we have to only be concerned on the in degree. So for in degree, there is no in degree. For S, there is one in degree. For U, we have one in degree. Yeah, out degree is 1 here. So only one in degree we are writing. So in degree is 1. For P, in degree is 2. For Q, in degree is 2. For R, in degree is 2. We can see this one and this one. Okay. And now we have to find the topological sequence for that. So we start from the that vertex which have in degrees 0. So this is a DAG, so surely it contain a vertex which have in degrees 0. So T is actually the vertex which have in degrees 0. Okay. So now what we can do, we start from here and we'll remove that. We'll remove the vertex T which have in degrees 2. So remove the vertex T from the topological and add in the topological sequence. So topological sequence is listed out here. So T we just remove now. T will once we remove, so and also update that. That's the meaning of we have to update. So once we remove that T, then the previous one is once we remove. So once we remove, the edges will be also removed. So that means the update of U for in degree is 0. For update of yours in degree is going to be 0 because there is no in degree for U, and S will remain as once you remove T. So order is now, this is the sequence I will write here. So T is the first one, U is become 0, and U in degree of T S will become 0. Now this is now again you can think this is a DAG, and again which have 0 degree, you have to remove that. So either we can do it for U or we can do for S. Okay. Now vertex U and S have the in degree is 0. Remove any one of U and S. Both have a in degree 0. We have to remove that. So once we remove, so top like we remove U is here. So in the sequence T, now next is going to be U, and we have to now remove U. Once we remove U, we have to update the all in degrees. So once we remove this one, so this is the part will remain, and the in degree of P become what? From 2 we removed 1 edge, so it will become 1 here. So we can see for P is become 1, U is already 0. This all are the remain same. Now this is a DAG. Now in this DAG again the in degree is 0 for S, so we have to remove S. So in the sequence the S will, the next is T U S will come. And once we remove this one, we have to update the rest all. Like for the update for P we become 0 and for R become 1. Okay. Now the next one is we can see it here. For P becomes 0 and R become 1. Q will be as it is. Now again this is a DAG and this is in degree is 0. We have to remove this one. Okay, and you will add in the topological sorting. So next is going to be TUSP, and now we will remove P is here. So once we remove P, again this is a 0 and this will become 1, and again the next is we will remove R and then Q will removed. See here we can see that the TUSRP, and we have to remove Q. So topological sorting finally we will get TUSBRQ. This is the topological sorting we'll get here. And this is, yes.
Sir, what you have shown, but I have not done in this way.
By which way you did?
Sir, just by looking at the questions that US is before T and SP is before R. That's why I am just putting the letters and the TUSPRQ come. Is this the right way? What I have done?
So suppose this is a simple one, that's why you able to do this. Otherwise, it will be more complicated. Then you have to follow the algorithm. At least algorithm you have to follow. This is a simpler one. You are able to, right? You are able to exactly get the this one. Like here is here is not like more edges is not here, no. So that is easily to do that by looking there. But by this is an algorithm. So whatever we just now discussed, this is an algorithm. Okay.
Yeah.
By this way you can do if it is the more complex graph.
That's why I'm asking that is this the what I have done is the right way? I think
so for simpler graph it could be done, but if you go with the this way it will give the accurate answer, no?
Yeah. Thank you.
Sir?
Yes.
This after T, U and S are interchangeable, no? We can go for S first.
Any one of them. Whatever the after T which have 0, either we can go with the yes. So here is this one, no, U and S can be interchangeable here because both in the starting you can
Excuse
see
me,
both
sir.
have DAG. Yes.
Sir, will you be taking doubts after the slides?
Yeah. So now the slides have finished. Now the final thing we are done. So this is the slide is done. So doubts you can now ask.
Yes, actually, I do have doubts in week 10.
Okay.
Concepts of independent
so-
set and
Yeah. So yeah, like one by one, please one by one take your doubts. So Subhranshu is the first one. So what's your doubt, Subhranshu?
so concepts of independent set and vertex cover.
So independent set is very quickly we can see, like suppose if you have a graph A, B is here, C is here, D is here. Okay. So independent set means we want to find independence means we have to find a set of vertices. We have to list out the set of vertices such that edges will not, whatever the we will find, no. So whatever the list out, we will list out the vertices that in between there will be no edge. Like suppose I just suppose A I wrote. Okay. Then A if we took vertex A, then B cannot be written because there is an edge. D cannot be, C cannot be. But here let me write the next one is, here is F. So we cannot write in the list here in this set, not B, not D, not C, but yeah, we can write F. So this is an independent set for this graph. Okay, different independent set is also possible. Let's see here, like I just started with A. Okay, suppose I took this set. First I took D. So from D once I took, so I cannot take A, I cannot, okay, from D I cannot take this B. Okay, so but we can take D, sorry, C, because there is no edge. So C. Now C, and also I can route, there is no edge F. So F could be. So this is an independent set in the for this graph. But what is going to be the maximum independence? We want to find a set of vertices such that it will be the maximum number of vertices can be covered, and also that is going to be independent. That is the some problem we have.
Yes, sir, there is a problem about maximum independent set.
Yeah. So like for this graph, we actually find like this is an independent set, but it is not in the maximum form. This is going to be in the maximum form, or is there any other one? Like if we choose F, then we cannot choose C, but we can take A. Okay, once we take A, or we can take D. Once we take here A, then we can, for D it could be correct, but for we took, once we take A, we cannot take here B, and we cannot take here D. So this is F and A is only in that case. So for that case, order, matrix is, set is
similarly that D and C, either D and C is acceptable, no, sir? F cannot.
Yes. So this is not an order. This is it is not in order because this is a set. So independent set. So either any order it could be possible. So maximum independent for this graph is this one.
So no, only D and C will be there in the independent set. How F will come?
Sorry. Here is, we took C here, so we cannot take F. So this is not going to be F here. Sorry.
Yes.
Because there is a mistake that because F I will take, then there will be edges possible. So I have to find such vertices. We have to find the set of such vertices so that no one is connected. Okay, this is the one. You are listing out the set of vertices. So whatever the list you have taken, or whatever you have set you have taken, in that no two vertices will be connected with an edge. This is an independent. And vertex cover is a different. Vertex cover is actually cover the edges. Means whenever you have any problem, okay, always think with the installing of a camera on. These are the corridors you have, and you want to install some camera. Always you can think for this vertex cover. Suppose you want to, any problem you have, you can, your own mind, you can think you are in a hotel and you want to install some cameras on the corridors so that the maximum number of edges can be covered. Okay, that's the here maximum number of edges can be covered. So here is if we install here on this vertex say, so in the vertex cover is actually contain the set of vertices is actually take that. So if you install here, so for A, if you install A here, so it is this one is covered, this one is covered, this one is covered. Okay, so now next one is what we can install. And actually we want to cover the all edges, no? So where we can install so that this will cover, this edge will cover, and this will edge will cover. So if you install here B for this at B, then this will be only covered here. Now if you install F or C anywhere, so if you install F, so this is going to be now full cover.
Sir, so in general, we can tell that vertex cover is the edges that is connected to a vertex.
Means here is vertex cover means you are trying to cover, we are trying to take those vertices which cover the edges. Like we suppose you are in here is I took here, suppose I install or I took this vertex. That means by this vertex, this edge is covered, this edge is covered.
Yes, sir, got it, got it.
These two concepts you have. Yeah, let me go with the next one.
Sir, another doubt question is there. Practice assignment week 10, question number 1.
Okay.
Sir, can you explain it in DFS and BFS in both the models?
Suppose we obtain the following DFS tree rooted at 0 for undirected graph if the vertices are given here. Which of the following cannot be an edge in the original graph? So this is only we'll do for the DFS. Okay, we are not going to discuss for BFS. Only DFS because this is the following DFS tree is said. No, so we are only consider for DFS only.
Yes, sir.
So when there will be an edge in DFS, we just now discussed. If it is in the same branch, then there is possibility that, or then there is possibility that there could be an edge. If it is if two vertices are in the different branch, then there will be no edge. There will be no edge directly. You can say if it is like here, like if you think 3 and 4, they are lying in the different branch. So 4 and 5 are actually not connected. So there is no edge between 4 and 5. This is the mean of for the DFS.
Okay.
Branch concept is for DFS, level concept is for BFS, for the edge related to an edge. Okay. Sorry.
Yes, sir. Yes.
Excuse me, sir.
Yes.
Sir, then in that case, 9 and 10 won't be like won't have a edge, right?
Yeah, there will be no edge in
2 and 9 will have an edge.
2 and
9.
2 and 9, yes, they are actually lying in the same branch. So
yes,
there could be possibility that there is an edge.
Okay, sir. Okay.
Okay, so now from here,
if there had been given a BFS tree, so how to find this question?
So suppose if this problem is for BFS, so yes, like here is, now we start counting the label, no? Like this label is 0, this label is 1. Okay, and this label is again 1. So 1 and 2 here is on the same level, 1, 1. Okay, but here is for the level 3. So level 3 is here. Okay, so here is level 3 is on the level 2. 7 is again the level 2 because of this one. This is level 1. This is level 2. 6 is on the level 2. So let me write just a minute. So here is where is that? Okay, so this one, like you can draw a line. This is a level 1. Okay, this is on the level 2. This is on the level 3. These are on the level 3. Like you can count. This is the level of 0. Like here 0, 1, 2, 3. So these are the vertices which is on the level 3. So now if you count the edges with respect to that, so there is a possibility that whatever in the level 1 and level 5, there is possibility that there could be an edge. But in the situation of like 0 and 3, if you think, 0 and 4, in the case of 0 and 4, so there is no edge in that case, because if you do the difference, no, here is do the level difference 0 minus or 3 minus 0, which is going to be 3, or also for level 2 also 0 and 2, there will be no edge. Like from 0 to 2, like 0 to 3, there will be no edge.
Sir,
Yes,
except 1, there will be no edge with 0.
Except 1, there will be no edge with the 0.
And for 1, we will there will be no edge except 2 and 0. For 1.
For 1, the level difference is like here is what is the level differences for 3 and 2, which is going to be 2. So for this one, there is no edge with this one, no, this 4. There will be no edge in the DFS for 1 and 4, because level difference, you can see level difference for 1 is 1 and for 4 is what? 3. What is the we just now saying? If the vertices of I level can be possibility have an edge, I and I plus 1 have the possibility an edge, but I and I plus 2, then there is no edge for the DFS. And for the branch case, if it is like here in the same branch is lying, then there is possibility that there is an edge. But between 3, 4 and 5, or 5, 8, or 9, 10, or 9, 6, or 7, 6, there is no edge in that cases. Different branches, but this is for DFS and this is for BFS. Okay, is it clear now?
Yes, sir. Yes,
sir. Sir, I have small doubt in the same question. So for DFS also, like the level will be same, right? What's the difference here in the same?
Why you are again we confuse? DFS is branch. DFS is for branch only. Can you tell me 0 and 10 or in the same branch and different branch?
Same branch.
0 and 7 and 10 is in the same branch or different branch?
Different ones.
So if there is a different branch for a DFS give the branch case. Okay. For a DFS case, okay. For a DFS case, we have a branch case, and for BFS we have a BFS. For we have label case. Okay.
Okay. Sir.
Now is it clear?
Yes, sir. In that question, 2 and 9 is in same level, or I mean same branch or not, sir? 2 and 9.
2 and 9. So 2 and 9. So it is in the same branch, no? If you draw like this is continuous is coming.
Okay.
In the same branch.
But
this is a root one,
0.
no?
Yes, sir.
This
even 0 will be considered, right?
It is even the 0 is like following the same branch.
But 1 we cannot say, sir. Like
1 is not going to be.
Oh, sir, but 1 is connected to 0 and 0 is connected to 9, so we cannot say that 1 and 9 are same.
Here is the root kind of thing is happening. Here is this one is root. These two are branch.
Okay. Okay.
Sir. Sir, except that 7 and 10, all the options will be right, no, sir? For this question.
I have to check like 1, 4. Yeah, there could be 0, 4. Yeah, there is a possibility. 7, 10. 7,
yes,
10.
Sir. There is no possibility. And 2, 9, there is
9,
possibility.
Yeah, there is a possibility. So which option is going to be correct for this one?
7, 10 only.
Only 7, 10, no?
Yes, sir.
Yes. Okay. Now let me go with the next one is Ronak. Ronak want to ask. Yes, Ronak.
Hello, sir. I have doubt in 10.1, question number 3 and 4.
10.1.
Yes, sir.
One and 4.
3 and 4.
3 and 4. Okay. So for 3, we actually, this problem is we want to form a suppose this information is given, we have to convert that problem in the graph form.
Yes, sir.
So here means if there is a resistance, then there will be an edge. And if there is an edge, this is a wire, then you can think it is a vertex.
Okay.
Okay.
Yes.
This is the information. The electric wire having a resistor can be represent an edge. So resistor, like here, what is the resistor is there? Okay, this is going to be an edge. This wire is actually going to be vertex. So if you see that it have 3 resistor, so here is 3 vertices and 3 edges. So 3 edges it has. So now we can think like 1, 2, 3, 4, 5, 6. So 6 vertices means a graph contains 6 vertices. Okay, 1, 2, 3, 4, 5, 6. This graph 1, 2, 3, 4, only 4 graph. 1, 2, 3, 4, 4 vertices. 1, 2, 3, 4. Okay, 4, and this is okay. I think I'm missing something. Okay, this is okay. This is can represent. Okay, sorry. Oh, sorry. This represent an edge, no, and the edges. This wire represent the vertex.
Yes,
the
sir.
resistor can be represent an edge. So how? Okay, this means this is one edge. This is 6 edges are here. 6 resistors here. 6 edges. So 1 and okay. See 1, 2, 3, 4, 5. So this is 4 only. Sorry, 5 only. I think this is okay. 1.
But in the answer, it is showing that answer is A.
Okay, just a minute. Let me count it here. So that means edges is represent the 6 edges it have. From here we actually 6 edges. 1, 2, 3, 4, 5, 6. So in this, the first graph have 6 edges. In this graph, it doesn't have 6 edge. It doesn't have 6 edge, and this one also. Okay, only the graph we have
6 edges.
This one, no, resistor represent the edge, no. Here is
so above diagram.
Sorry, for this diagram.
Okay, sir.
This resistor represent an edge. So one edge, second edge, third edge, fourth, fifth, and sixth. There are 6 edges. So which graph represent this? Which have contain the 6 edges. Okay.
Yes, sir.
Okay. The next one is.
Sir, I have one more doubt. Number 4.
A graph V is shown in the figure this here. V is a set of nodes in the graph E, and E is the set of edges. Choose the set of correct. G is an undirected graph. G is directed graph. So V4 is reachable from V1, V2, V5. So what is doubt here?
Sir, I want to know how can V4 is reachable from V1, V2, and V5.
So V4 is reachable from V2, V4, and V5. So V1 is where? V4 is where? V4 is where? This is V4, and this is V1, V2, and V5 is where? V5 is. So from V4 we can go here. Okay. From V1. So here is, see that 2 direction. Here is the 2 direction is given. So from V1
V4 can reach V5, sir.
V4, no, here is V4 is reachable from.
Okay, sir.
From is there. Okay.
We can
from 5 to
V5. Okay.
Like here is from V1 we can go V0 because there is a 2 direction is given. From V0 we reaches, and from here also two direction is given, both sides is direction. So V4. So from V1 to V4 we can reach. From V2 to V4 also we can reach because this is also a both direction is there, and here is already. Is it clear?
Yes, sir.
Okay. Sir, the last question.
Okay, what is the last one?
That you in the question this before you were explaining, sir.
Only this
I
one.
could not get it. No, sir. The question last this
Sir, he's asking
In
about
this
the
problem is we have this graph is given. Oh, electric
no,
one.
sir,
So electric one is
I cannot
actually here is what is given here. Only this information is enough to solve an electric wire having a resistor here. Okay, or you can say
yes,
resistor or resistor, whatever the word is. Okay, can be represented an edge. So whatever here is, this is a resistor. Okay, this represent an edge.
Okay.
So
Okay,
how
sir.
many edges will be possible?
1, 2, 3.
6 edges.
There are 6, sir.
So 6 resistors are here, means 6 edges. So which graph contains 6 edges? You can count 9, right? This one is only 6. Otherwise, this is 5. No, this is 5. This is 4. This is 3. Right?
Right. Okay, right, sir. Got it.
Next is 29XB or no, Agrawal, or no?
The answer is first one, sir. Answer is first.
Yes, first one. Or no is the next one. Yes or no?
Yes, sir. Sir, I have doubt in activity question 10.2, question number 3 and 4.
Three and 4. Find the minimum possible number of computers for the tournament. So what is in this problem asking?
Sir, this is vertex coloring problem, sir.
Vertex coloring problem?
Yeah. Minimum 3.
A minimum number of possible minimum number of computer is required. Means how will like if you see that is for the
For the second question, the third one is the answer, sir. For the second question, the third graph is the answer. So based on that is based on this one is the third one.
Okay, so whatever this information is given, no, based on that we have to try to draw the graph. So for like fortnight is from 10 to 11, so do TA is from 10:30 to 11:30. So there is an edge will be, if the classing is there, then there will be an edge. If
Sir,
there is a class,
we can make it on number answer time period, and that overlapping will be
given
excluded.
edge.
And,
yes. So like
on number line, the time period given from start to end. Window is given, we can mark it on number line.
So
and,
suppose I think this is going to be the graph here, no? This is going to be the graph. And now the color is number of colors.
So option C is the graph.
Option C is the graph, sir.
Okay, this is going to be the graph. So now for this one, you need to find the minimum number of color is required. Like here is now color this one, then you cannot color these two. So coloring is there.
Okay, so we color the non-common. We color them, and then find the number of different colors.
Yes, find the number of different color.
So, like if there are 3 different colors, so the total number of computers required will be 3.
Yes.
Got it, sir. Answer question number 4.
Question number 4 is independent set is asking. No, question can be solved. Okay, in a college we sent a sport team for a sport festival in order to festival in other college. The team is multi-talented. Okay, there are many students are skilled in the different sport. Okay, Okay, they cannot be part of team of two different. Okay, however, the same individual cannot be part of the team of two different sport because of the possible clashes in the timing. A graph is shown here. Okay, the edges here is created where the nodes are the events and edges can connect the pair of sports. So here is the nodes is actually the event, like this is one event, this is another event, this is another event, and the edges is the connect with the sports where the team is the edges can connect pair of sports where the team members share the team member, like between two events or between two sports. Like here, this suppose this is an event which is a sport and this is another. Okay, so between these two there is at least one player which is playing in both. This is the graph. It actually shows that in the college wants to team member of to take the part in the maximum number of sport, then choose the correct option. So by which way we can solve so that the maximum number of sport team member to take part in the maximum number of sport. Okay, so maximum number of sport, the team members are actually how we will solve this problem so that the maximum number of team member can play in the maximum number of sports. So how we will solve this? Maximum independent set or minimum size vertex cover or minimal coloring. Already it is the word is also included. You can see that the maximum independent set is what for the non-connecting edges. No, if it is once you choose this one, then you cannot choose the next vertex. You can choose this one. And actually, because of classing timing, you have to choose actually such that then so that there is no difficulty will happen. And we want to find the maximum that we have to try to maximize that. If it is the edge will be, then classing of time will create a problem. So we have to do like that so that there will be no clashing and the maximum possibility of sharing members can be done. Like if it is this one is that, then this could the sport can be played with the same person. Correct?
Sorry, sir, I did not understand that.
So, sir, here we should have to not consider this inside edges, sir. If you remove the inside edges, the answer will be right, sir. Maximum number of sports in which 6, it will be 6, sir.
For that, we have actually we have to find the maximum number of independent set. In this graph, we have to find the maximum number of, because the maximum number of between two events. So this is one event, this is one event. Okay, this is one event and this is one event, and this line says there is a sharing of the person, but because of time clashing, we cannot. Because of time clashing, we cannot perform. There is a time clashing, we cannot perform, or a person cannot perform in the same sport. So we have to do something different. So if you suppose this event is happening, okay, and suppose one person is playing here, so he cannot play here. He can suppose one person is here. This sport is happening here, and this is another sport is happening here. So there is no person in that involved. There is no person involved in that. Sorry, there is no person involved here. Okay, mute. There is no sharing member or there is no two person is involved here. But we want to find what is that. College wants the team members to take part in the maximum number of sport. So here is no two, or in between these two sport, there is no person involved. Okay, there is no person is sharing. Then maximum number of sport we want. Take part in the maximum number of sports. So which sport, like if you choose this sport, then we cannot choose this sport, but we can choose this sport. And the members is actually here in that edges. No, I think I'm not explaining a better way. Or differently, you can think the maximum independence, it like maximum independent is the only the independent set, you know, independence is try to find the number of independent set, and maximum independent set is what? No two edges. We have to list out the vertices such that there will be no edges in between that. And here is we have to find the maximum number of spots. You can think by this way. We have to find the maximum number of sports, means here the events, these are the events. So how we'll maximize that? Only the independence that we have, no, the concept that to maximize that. Otherwise, minimum vertex cover is there, minimum number of coloring is there. Our rest are all for the but the independent set is for the maximum. Am I audible?
Yes, sir.
Sir, why option C?
Sorry, I just muted to all.
Sir. Hello. Sir, why by coloring we cannot get that? Why option C is wrong?
Okay, so by this minimum coloring, no. So minimum is again we are trying to minimize the number of color. You can think that by this word also, but we want to find the maximum number of spot.
Okay.
Sir,
they require maximum output.
In that case, sir, we'll have the two events on the left one, the two events on the left one, and the two on the right, and then the top of the triangle, and the second one on the right, after the top one.
Yeah. So whatever the independence, how many maximum number of independence set is going to be for this?
According to the maximum independence set, there are 6.
So 6 may be going to be that.
Okay, sir. And sir, I have more questions and other activity questions. Shall I?
So let me. Sudhir is the last one. Let me go with the Sudhir. Then that would be good. What's your doubt, Sudhir?
Yes, sir. I have doubt in 10.7, sir. That question. Only question is there.
10.7. Oh, this is active. Oh, we were discussing this one, no? In starting, we are discussing.
Yes, sir. Perhaps I am unable to get the question, sir. I am landing to the answer number 1, option A.
Option A, but see again in the simple word, when will be the forward backward edge, or what is the forward backward edge?
Sir, I am unable to get this statement given as per the alphabetical way.
Alphabetical means in order to like A you did, then B, then C, and then D or B. So in the order, like you cannot go with the like, or like you suppose you are at C, okay, then you cannot go with the B. Whatever the order you have, in that order you have to we have to explore the unvisited neighbors.
Sir, if we are going for DFS from A, starting from A, first we'll go to B. We cannot go to D. We will go to C. As per statement.
Yes.
Then to F and then to D.
Then to D. Okay.
Okay. So it is CF.
Sorry. So CF is what? CF is actually lying as a tree edge, no? CF is becoming a tree edge.
Okay, we call it tree edge, no?
Yeah, but we don't want the forward backwards is actually not a tree edge.
Then what is what we call, sir, forward edge?
Forward edge is like here AC is happening, in the same, like in the order we are going to A, B, and C. If you draw the tree, no? If you draw the a tree here, which is A, then B, then C, then F, and this here is T. So see that in A, B, C, D, F or D, sorry, F and D is here. So see that there is an edge, no? If it is in the line form, then it is like this. There is this is an edge, no? This is in the forward case.
Yes, sir.
This is an edge for in a forward case. Backward edge is generally response for the making a cycle.
Loop, cyclic.
Like for this problem, what is D here? D is backward edge or forward edge, like sorry, BD. What is BD is? BD is forward or backward?
This is forward edge.
This is forward edge because as you can see that here, where is that? This is B, D, C. In the same is it in the continue form it is happening. No, this is in the forward case is happening.
Yes.
Like this. If it is in this form, if I wrote, suppose, so A and then B, okay, and then B, then C, then F, and then D is here.
Okay.
So AC is there. This is the forward edge, and B and D is there. This is the forward edge, right?
Okay.
So that's why, and CF is not a backward or forward edge because this is it is happening in the tree form, no?
Okay, but in original graph also the C and F is connected. So
in the original also it is connected, but in the tree also it is connected. Sorry, it is in this, it is in the tree also. Okay. Okay. Arno have some doubt. Okay. Yes or no?
Yes, sir. Sir, in activity question 10.3, question number 3.
Question number 3. Choose the setup correct based on this. So the graph has 5 nodes. What's your doubt here?
Sir, actually, I did not understand how many degrees are going to be there.
So how many degrees is sum of the degree of all nodes is 20. Okay, so
How are the sum of all the nodes 20, sir?
So that's we have to check, right? We have to find, like here is, then you can make a graph for this, no? You can easily make a graph for this one. What is going to be the graph?
Sorry?
We have to make a graph, no?
Yes, sir.
Sir, and there is a formula also. If there is some edges, then the sum of the, sorry, if there is a degree of n, of degree n, then the sum of the degrees will be 2n.
Number of edges, no? If we have the number of edges is m, then some degree is 2m.
Yes, yes.
So we have to find the number of edges. If you find the number of edges in the graph, then sum of degree is going to be 2m. So how many edges we have in this graph?
5.
5, no?
Yes, sir.
Then the sum of degree is going to be 2m, which is going to be 2, 10. 10 is going to be, 2, 5, 10. Which option is correct?
10, sir.
This is some degree term is actually in the complexity, I think so. No, the term is, or also you can find the different ways. You need to find the graph and then count the number of degree.
Okay.
How many
sir.
vertex you have to count that?
Okay, sir. And sir, activity question 10.6, question number 1.
If we perform BFS in the directed graph G, how many times do we check whether a vertex U is visited? If we perform VFS, okay, in a directed graph, how many times do we check whether a vertex V is visited or not. Is 1 or is equal to in degree of V, out degree of V, or 2. So we can form this with the example, no? Like suppose this is the directed graph we have, or itself this one. Is that? Let's say this one the same. Okay. So what it says, the problem says, if you perform BFS in the directed graph, how many times do we have to check vertex, whether a vertex is visited? How many times we have to check? Suppose this is the vertex we have. So how many times we have to check is this vertex is visited or not?
In degree of visit.
In degree, right? Because either we go with this one once we have checked, and we with the level, like we go with this way and then this, then another times we have to check, right? So number of in degree give the number of times, how many times we have to visit that.
Okay, sir. Got it, sir. And sir, activity question 10.9, question number 1, 2, and 3.
You are the only one, I think. Okay, 10 people are here. Okay. 2 and 3.
1, 2, and 3.
1. So in this problem, we have to draw the graph, right? With the using table. So here is actually, what is that? It is in the, I think, a spreadsheet it says. Okay. So here is, once you open A, B1 means in the cell, this cells, that means here is whatever, like here is, this is A and this is B, 2 columns we have. So A1, this is A1 column. This is what? In the say, what it says, A1 is there, the I represent the row. So if this is in the first row, what is this? In the first row, and what is that? Second column, right?
So, no, sir. Actually, the A1 is the value of A in row 1, and in B1, that is A1 square. It says that the value of B1 is equal to value of A1 squared. A is 1 squared.
Oh, let me read out that. What is that? In the entry and its dependencies in the cell in spreadsheet can be represented using the direct acyclic graph. Q10 shows the part of spreadsheet. The particular cell in a spreadsheet can be represented as xi, where x represents the column. Okay. Oh, this A is represent the column and I represent the row. The entry A square I or A2I is the cell. The entry in the cell B1. In the cell B1 means B1 has the value this one. Okay, this is okay. When has the value, okay, in B1, where A1 is the value in the column A, row 1. Entry this one in cell B. So in cell B1, this is B1. So this value is actually, so this entry is actually in cell B1. Cell in B1 means B1 has the value. Okay, this is the value, and where A1 is the value in the column. Okay, so these are the value is actually written. Whatever the spreadsheet is exactly, these are the values actually written. Okay, which of the following graph represent the dependencies between the cell in the column? So this is column A, this is column B. Okay, and this is row 1. This is row 1 is written A1, and this is A1 square, you can say. So in the cell 1, this value is 1, and this is in cell B, this is square. So what is the dependency is here? There is a dependency is happening, no? In cell B1. In cell B1, there is a dependency with the A1.
Yes, sir.
Because it is a square, so there is a graph, so there is a edge will be in cell in this cell, which
A2.
is A2. A2 is the value is obtained from B1 minus n. So this is B1.
Yes, sir.
B1 value is A1 square. So this is going to be A1 square minus 10. So that means there is an edge going to be from B1 to A1.
A2.
There is going to be B1 to A2.
A2.
B1 to A2
A2.
we have. So which is going to be B1 to A2 we have.
Yes, sir.
So by this way you will try to draw the graph one by one. You have to substitute the values also, so that it will be more clear to you. Like this value is B1, no? So B1 value is A1 square. B2 value is, you can substitute here.
So in that case, for B2 it will be independent, and then in A3
B2 is going to be independent.
Okay, so in A3 will go for A2 and B2 both. Both of them
A2
will.
and B2. So A2 is here and B2 is this one. So
Yes,
that
sir.
means
So both
A3
of them
is
will
going
have
to
an
be
outgoing.
connected.
So both of them will have an outgoing to A3, right? And then B3 will have B2 and A3, both having an outgoing on B3. Okay, so
like here is like this is 1, 2, 3. So B4. This is B4. So B4 is actually depend on B2 and A3.
Yes, sir.
So that means there is an edge to B4. There will be an edge. B from where? B2 to B from B2 also and from A3 also. So B4. So B2 from B2 also and A3 also. A3 is where? So which is going to be A3? So this is B3, no? This is B3. So to B3. So where is B3? Here is B3 from B2 also and A3 also. Sorry, where is that? B2 and A3 also. So we have that. So like this, you can verify.
Okay, sir. Answer question number 2 and 3.
If the values B1 increase by 10, then value is, so that is on totally depend on here. No, this is the value. Just need to verify that. It is totally on dependence.
But sir, how are we going to verify that? Like, in they are asking like if the B1 increases by 10 times, then what will the value of B2, right?
So what is going to be value of B2? B2 is
independent.
totally independent. Then you have to choose.
Okay, so it will not change. Okay, so it will not change. Right. Got it. And if there is change in B2, then the reason is none of the above. Then none of the above. Okay, none of the, because it is independent, so there will be no reason for its change. No one will be responsible for its change.
Yes.
Right. Okay. So okay. Answer practice assignment. I have question number 1, 3, 4, 9, 10.
Then you go. I will suggest you go with the solution one. Because
Practice
solution is
assignments.
already uploaded. Yes.
Where in supplementary content?
Yes, it is week 10 practice assignment solution is already there.
Okay.
Okay.
Okay. I'll refer to it. If I still have problem, I'll attend tomorrow's session, right?
Yeah.
Okay. Okay, sir. Thank you, sir.
So now I'm going to close the session also. It is 3:30 hours.
Sir, I have doubts, sir.
So can we close now? Because what's your doubt? I will take your one doubt only.
Sir, I have 6 questions, sir. Totally.
6 questions.
Yes, sir. All across the week 10.
All across, but now see only the 7 participants is only, and see how long I will teach. No, this 3 hour 30 minutes already reaches.
Okay, so just one question, sir.
Yeah. So which question number?
Activity question 10.1 question 2.
10.1 question number 2.
Yes, sir.
So what's your doubt here?
Yes, sir, you have to explain. Can you please explain the questions?
So you are not getting what is the problem here?
Yes, sir, problem.
A person A is a job applicant while another person B is hiring a manager. Okay. A person A is a job applicant while another person B is a hiring manager at a company. Okay. Although both of them are the member of the website LinkedIn. Okay. A is not directly connected to B via the website. So A and B are not connected on LinkedIn. The network of A and B are shown in the graph below. Okay. Choose the option which shows one of the shortest part of the connecting A to B. So which is going to be shortest part here? What is doubt here?
Sir, I have a doubt between 2, 3, and 4, sir, option.
2, 3, and 4. So what is the problem? Like I want to find the shortest part between A and B, no? What are the paths between A and B? A is here and where is B? B is here.
Yes.
So by which path you will go, this way or by this way or by there are so many possible ways, right?
Yes, sir.
But we want the shortest path. So which
Yes,
is, there are so many paths we have, we want to find the shortest path. So which is going to be that, like by this way? So that is, you have to choose now. You have to connect, like count which one is the shortest path.
Okay, sir.
That is just for counting.
Sir, an activity question 10.2, 2 and 3, sir.
So I will take later now. Now I just said I will take your one doubt. Okay. We'll now
Okay,
take
sir.
because I almost 3 hours 30 minutes. Okay. We'll take later your doubt.
Okay, sir.
So thank you so much.
Thank you, sir.
Thank you, sir.
Thank you, sir.